Yeah, good morning. So we'll start with very brief review of what we have discussed in the yesterday's class. Okay, so we have started the very important topic, which is semiconductor theory. Okay, so again and again, I'm mentioning semiconductor theory. If you understand, okay, then the other device characteristics, other devices that we are going to take up is going to be easy for you. So please concentrate on these basics. Okay, and that is the reason. Okay, we are going to discuss this semiconductor theory in detail, starting from very basic things we are going to discuss. Okay, and that is what I am trying to do here. Okay, and one more thing, one more suggestion or request from my side. Please do take the notes. Don't forget. Okay, don't simply sit and listen to the class. Okay, you try to not try to. You have to take the class notes. Okay, so don't forget it. Okay, now, so we have started with in the semiconductor theory, the first topic that we have considered is the equilibrium carrier concentration we need to discuss. So in that, for our convenience, we made into three subtopics again, starting with the basic concepts. Then we need to discuss about the intrinsic semiconductor and then extrinsic. So we have started with the basic concepts. So in that, okay, so what we need to discuss is what are the different types of semiconductor materials, okay, that are possible, and then we need to understand, okay, what are the terms that we are going to use frequently, what it is equilibrium and steady state. And also we need to understand what is wave particle duality. Okay, so that is what we are going to do in this basic concepts. Okay, and anyhow, intrinsic and extrinsic we'll consider it later. So we have started with different types. Okay, start pure semiconductor, one way of classifying it, then intrinsic, extrinsic. The other way of simple, also called as elemental. The other one is the compound semiconductor material. So simple or elemental is also called as indirect band gap semiconductors, and compound semiconductors are also called as what? Direct band gap semiconductor materials. So the important point that you have to understand here is how we are defining the intrinsic semiconductor material. Okay, so in the pure, the name itself is giving there should not be any defects or impurities. Is it fine? But in case of intrinsic, there can be some impurities and defects, but what is the condition? The number of electrons and holes must be same as what in case of pure semiconductor. So this is possible if one impurity is compensating the other impurity. Okay, yeah, this is what we have considered. And then anyhow, again, this classification you can understand. Then we have defined what is meant by equilibrium, or we can also call it as thermal equilibrium or thermodynamic equilibrium. Simply you can call it as equilibrium. Okay, so what it is, if I want to say a semiconductor is in equilibrium with its environment, obviously what is the condition? For every process that is going on between semiconductor to environment, there is an inverse process at the same rate, and this also applicable within the semiconductor material. Okay, and we have given how we can check this. There are two conditions that we need to check. That is, there is no external excitation, but other than can be an excitation here. And second is what? Sorry, there is no net transfer of energy or charge. Yeah, here in the second point there is a very important thing that you need to understand. I am not saying that no transfer of energy. Okay, what it is? No net transfer of energy. This is very important. Okay, because once your temperature is greater than 0 Kelvin, always there will be flow of charges, definitely. But what I'm saying, net, that word is very important one. Okay, and we have seen some examples also. And if I want to use your semiconductor, definitely you need to disturb its equilibrium condition, then only you can get something out of it. Okay, and some of you have raised how, then what is the use of equilibrium and all. Will you can get to know those things once you start analyzing the devices. Okay, because you need to first do the equilibrium analysis for any device, and then you go for any biasing or any other things that you are going to consider. Okay, yeah. Then we have defined what is meant by steady state. So what is this steady state? All the processes are going to be constant with respect to time, or there is no variable or process that is going to vary with respect to time. That is what we have defined, and we have given, okay, relation. Okay, that is, if a semiconductor is in steady state, it need not necessarily under equilibrium condition, but if it is in under equilibrium, definitely it is in steady state. We have given example and we have explained this also. Okay, and one more important point you must understand here, whatever we are going to consider practical situations in the device analysis, we can take it as quasi equilibrium. Quasi means small deviation. Similarly, transient conditions, that can be considered as what? Quasi steady state or quasi static. Okay, and that is what we have seen. And we have seen the wave particle duality. You know very well that energy or matter is going to propagate in the form of streams of particles, okay, or in the form of wave, that is nothing but traveling wave. Okay, and these are the things that we have discussed here. Okay, and then we have derived one important relation, okay, using the two equations. V is the energy here, P is the momentum. From that we got this relation. Yeah, yesterday I think I have written this wrongly, this relation. Those who have not listened, please correct it. Okay, 1 angstrom is earlier I have written it is 10 power 10 meters. It is not 10 power 10. It is 10 power minus 10 meters. Okay, please correct it. 1 angstrom is 10 power minus 10 meters. Earlier I have written 10 power 10. Please correct it. Okay, and based on that we have done the problem also. Okay, and we have started with the intrinsic semiconductor material. In this we need to discuss two types of models. One is called as the bond model, another one is called as the band model. So in the bond model we have discussed about the photons, free electrons and holes, how they are going to be present. Okay, now we have started the analysis at absolute zero, and we have made some important conclusion with that. Intrinsic semiconductor material behaves like an insulator, but you need to give at what temperature. This is important. Okay, it is at absolute zero. Okay, then we have discussed how the phonons are generated, then photons. Okay, and from that how the electrons and hole pair has been generated, and we have discussed about the hole, okay, and movement of the hole. So here in the concept of hole, you must understand that physically what is going to happen in the crystal structure is the bound electrons are going to move via the vacancies that are going to be present. Okay, and if bound electron is moving in this direction, we can very clearly see that the vacant position is going to move in the opposite direction. Okay, and you can very clearly see from the crystal structure that there are large number of bound electrons and very few vacancies that are going to be present. Okay, so based on that, okay, what we have given, how the free electrons and bound electrons are moving and how the hole is going to move, that is what we have discussed here. And then finally we have given, okay, the effective mass, because you can understand from this statement very clearly, we can see that the bound electron and free electron, they are going to respond in a different way with your applied electric field. Okay, and that is the reason why finally we got this mobility of electron is less than mobility of hole. Okay, and if that is the case, okay, we can have mobility. Okay, sorry, this is effective mass. I am sorry, what is this? This is the effective mass of electron is less than effective mass of hole. And if from this one, okay, we can understand very clearly that mobility of electron will be more than mobility of hole. Okay, mobility of electron will be more than mobility of hole, that you can conclude. Okay, anyhow, still we don't know what this mobility is all. We'll discuss in the carrier transport. Okay, hope I am clear. I think up to this we have discussed. Okay, now let us consider, okay, the next topic that we need to discuss. So what is that? We need to understand briefly here. We are going to discuss about electron hole pair generation and recombination. But anyhow, later on, we need to consider this in detail. Okay. Here I'll just give what is that mechanism is going to be. Okay. So try to understand it. Okay. So what we are going to consider now, electron hole pair EHP. Okay. Will represent with EHP. What is this? Electron hole pair generation. Okay. And recombination. Okay. Now, see, once the temperature is greater than 0 Kelvin, please try to understand. Okay, T is greater than 0 Kelvin, there will be thermal energy that is available. I'm sorry, there will be thermal energy that is going to be available. Okay, so because of that, always there will be generation and recombination of electron hole pairs in the semiconductor material, whether it is intrinsic or extrinsic. Okay, so let me write that point. Okay, for this case, always there is generation and recombination and combination of electron hole pairs in the semiconductor. So here semiconductor means it can be intrinsic or extrinsic semiconductor material. It's a continuous process. Okay, hope I am clear. Okay, so if that is the case, can I write like this? If there is a generation, okay, and there will be recombination. Okay, and it is a continuous process. Okay, generation and recombination is going to be continuous process. Hope I am clear. Okay, now we'll see what are the different possibilities. Okay, different mechanisms that we can get this generation and corresponding recombination process. Okay, so you can have the generation, the one as photo generation or photo ionization. What it is? Photo generation, or I can call it as what? Photo ionization. Yeah, if you see the name itself, you can very clearly understand here. Okay, ionization means what? You are removing one electron. Okay, and by what? Photo means what? Here you are applying the light energy. It's an obviously. Okay, or photo generation. So you are generating electron hole pair by applying the light energy. Then that process you will call it as what? Photo generation or photo ionization. Okay, hope I am clear. And once you excite your electron, again there will be a recombination process. Yes or no? So when it is recombining, the difference amount is going to be released as the light energy in this case. Then it is called as radiative recombination. Please try to understand the terminology, okay, that we are using. What is this corresponding recombination for this process? You can call it as recombination, radiative recombination. Okay, so what is the meaning of that? Radiative means you can observe the light energy. Again, not in all type of materials where you can observe this, in the direct band gap semiconductor material. Why and all we'll see it later. Okay, fine. Now the second type of possibility is, we'll call it as impact ionization. What it is? Impact ionization. What is the meaning of this impact ionization? The charge carriers will move with very high velocity. They releases electron hole pairs. I'll repeat. Impact ionization means what? The charge carriers will move with very high velocity or high energy. They will collide with the atoms. generates electron hole pair, and that is called as what? Impact ionization. Okay. The corresponding recombination process for this is called as Auger recombination. Auger recombination. Okay. Yes. And another possibility, phonon generation. Okay. Phonon generation, and correspondingly phonon recombination. Okay. Phonon generation, phonon recombination correspondingly. Yeah. Here, what you can, you can understand what are the different particles that are present. The different particles that are present. Okay. So we have started with phonon. Okay. Then it is photon, free electron. Okay. And hole. Yes or no? Yes. That is the why corresponding. Okay. So photon, you are applying the light energy here. From that, you are generating electron hole pairs. Impact ionization, you are generating electron hole pairs and corresponding recombination. There will be phonon generation, that is why atoms start vibrating, that you can take it as what? Phonon generation and phonon recombination. Okay. Hope I am clear. Why we are getting these type of things is there are 4 different particles that we have considered. Okay. Maybe later on we are going to drop this word free. We'll simply represent it as electron. Okay. Please remember it. Okay. Depending upon the context, you must understand. Most of the times, electron means in our discussion it is going to be free electron. Most of the times. Okay. So try to understand this. Okay. Hope I am clear. Yes. Now, if you see the recombination process, you can have 2 types of recombination processes. Okay. 2 categories. Recombination. Okay. You can have 2 different recombination mechanisms or properties. One is called the electron hole pair has been recombined. If you can able to observe the light energy as the output, you can call it as a radiative recombination. If it is not light energy, it can be called as non-radiative recombination. Okay. So you can have radiative recombination. Okay. Radiative recombination. And what is the other possibility? Non-radiative recombination. Hope I am clear. Okay. So in case of radiative, the name itself is indicating radiative recombination process, you can observe the light energy. What about non-radiative recombination? It is what? There is no light energy as the output. Previously we have discussed what is the here we have discussed the different types. No, let us name them so that we can refer it back. Let us take this is 1, 2, 3. Okay, 1, 2, 3. So out of these 3, we can very clearly see the first one is going to be, the name itself is giving radiative recombination. So I can list under this one, radiative recombination. Okay. And what about non-radiative? The other 2, that is Auger recombination and phonon recombination comes under this. That is 2 and 3. We can give the examples for non-radiative recombination. Hope I am clear. Okay. Yes. Now let us consider this recombination corresponding recombination processes. Okay. Now, photo generation, how you can represent? How you can represent photo generation? Yes. If you take the photo generation, The name itself is giving that you are applying the light energy. Okay, you can take H nu, which is greater than or equal to energy gap Eg. Okay, now it is incident on the where on the material, and it is generating electron hole pair. It is generating electron hole pair. So this process you can call it as what? Photo generation. Am I clear? Now what is the corresponding recombination process? Once the electron hole pair has been generated, now this electron hole pair may recombine, may not be with the same electron and hole, please remember, okay, because there are many number of electrons and holes, free electrons and holes. Now from this you can observe the light energy as the output. So what is this process we are calling? What is this? Radiative recombination. It is radiative recombination. Hope I am clear. Yes, okay. And if you go for impact ionization, just now I have given the charge carriers are going to move with very high velocity. They will collide the atom. They will release the electron hole pair. Now, the particle, charged particle means either it can be electron or hole here. Okay, so either electron or hole. Now let us consider either electron or hole is moving with very high velocity. Okay, and let us consider this is the atom that is going to be present. Okay, now electron or hole is moving with very high velocity. Now this is going to generate by colliding with the atom. It can generate electron hole pairs. Electron hole pair. Am I clear? Okay. Now what is the corresponding? This is nothing but what? What is the name? It is impact ionization. Fine. Now, whatever the electron hole pairs that are generated, again they are going to recombine. Okay. So there is a recombination. Now, in the previous case, the output is going to be observed as the light energy, but here it is not the light energy, but there is a difference. No, electron is at higher energy, is coming to the lower energy level. Okay, so there will be a difference of this energy will be given to some other electron or hole. Okay, nearby there will be some other electrons and holes. No, so that energy, whatever this difference energy is present, this energy will be given to either electron or hole. Please try to understand what is the energy is there. No, this energy will be given to either electron. Please, here electron means what? Free electron. Please try to understand. Okay, it is free electron. Okay, either free electron or the hole. So what is this process we have given? It is Auger recombination. It is Auger recombination. Okay, and what is phonon generation? If the atom starts vibrating, you can call it as phonon generation. And if it is not vibrating or stopping, the vibration is stop, then you can call it as recombination process. Hope I am clear. Anyhow, these things are very important for us. Okay, this radiative photo generation, radiative recombination, impact ionization, and Auger recombination, because later we are going to again. Okay, hope I am clear. Okay, so this is about briefly what is electron hole pair generation and recombination. Anyhow, these things again in detail we need to consider, don't worry. Okay, now here you need to understand one important point, that what will be the difference between recombination and scattering. Okay, very briefly we'll discuss again. In carrier transport, these things we need to discuss in detail. Okay, here I am briefly explaining. Okay, so what we need to consider: difference between difference between recombination and scattering. Okay, difference between what? Recombination and scattering. Here, both we can consider them as collisions. Okay. Recombination means what? Electron and hole are going to be colliding, as well as scattering. If you consider that also, you can take it as the collision. But what is the difference is, please try to concentrate. Recombination means electron and hole are meeting at a particular point physically, and after collision both the particles will be annihilated or both will be disappeared. Am I clear? I'll repeat the point. Recombination as well as scattering can be considered as both as collisions. In case of recombination, once the electron collision has been happened, electron and hole, they are meeting physically, and after the collision the particles are going to be annihilated or disappeared. Okay, but in case of scattering, there is no physical collision. It is going to be action at a distance, and the direction of motion of the particle is going to change. Okay, yeah, let me write the points one by one. Okay, so the first one is what we can say, both are collisions. Both are what? Collisions. Both are collisions. Okay, now in case of recombination, in case of recombination, okay, electron and hole meets physically, and after collision, both the particles are, okay, nothing but they disappeared. Okay, hope I am clear. Both the particles are annihilated. But what about scattering? It is not the physical collision, it is action at a distance. Okay, and the direction of flow of the particles is going to change because of either force of attraction or force of repulsion. Okay, let me write that also. In scattering, okay, it is action at a distance. Okay, action at a distance. Okay, and another important point that you must understand here is the direction of the direction of flow of the particles. Okay, here we are referring in general particles, but specifically what it is here, charges. Okay, that is electron and hole. Okay, flow of the particles changes due to either force of attraction or force of repulsion. Okay, yeah, let me write and I'll explain this. Okay, this point is very important to understand. Is this clear? Both can be considered as collisions. Okay, so in case of recombination, when there is a collision of electron and hole, there is a physical collision and both are disappeared. But in case of scattering, it is action at a distance, and the direction of flow or direction of motion of the particle is going to change. How you can explain this? Let us take an example. Suppose an electron is moving in this direction, for example, you take, okay, in the crystal, an electron is moving, okay, and a hole is moving in this direction, for example. Now, what is the force between the two? You can very clearly see they are opposite charges. There will be force of attraction. Now, what will happen? There will be a deviation for the path of this like this, and similarly, this also changes. It will move in this way now. Yes or no? The direction of flow is going to change in this way. So that is the reason why we are calling it as what? action at a distance, and also direction of flow of particle changes. Here it is force of attraction. Suppose you take an electron is moving in this direction, okay, and there is another electron which is present and it is moving in this direction. Now what will be the force between the two? Now it is the force of repulsion. Now this will start moving in this direction and this will start moving in this direction. Hope I am clear. Yes. Okay, so this is the important difference between what? Recombination and scattering. Okay, now whatever we have given here, example I have taken. Okay, so here you are taken, no, scattering is between electron and hole, here between electron and hole, sorry, electron and electron. Similarly, you can have scattering between hole and hole. So these things anyhow we'll discuss in the in the carrier transport in detail. Okay, so just I'm briefly giving what are the different possibilities, and we must understand, okay, difference between the recombination and scattering. Hope I am clear with I have given. Okay, later on these things we are going to consider in detail. Okay, so here I have given only between electron and electron, electron and hole, electron and electron. Similarly, you can have hole and hole, and also you can have vibrating atom. Once the temperature is more than 0 Kelvin, there will be vibrating atom. What is vibrating atom is called phonon. So now the electron which is moving in the crystal structure may collide with the vibrating atom. Nothing but what you can call, there is a collision between what? Electron and the phonon. Similarly, hole can collide with the phonon. Hope I am clear. Okay, so anyhow here I'm giving very briefly. Later we are going to discuss this in detail, because you need to understand this. Based on this, the mobility behavior you need to understand. Hope I am clear. Okay, yeah. Now we'll go for next topic in the basic basics of in the semiconductor, intrinsic semiconductor. Okay, we need to understand about, okay, so what is the next one? Concentration of electrons and holes. This is a very important one, because you must know how many number of charges are present. Okay, so let us consider that what it is we are discussing about now. Concentration of electrons and holes. So here electrons means what? Free electrons, please keep it in mind. Okay, and holes. Okay, yeah, again this part whatever we are going to discuss, again there will be a repetition. Okay, but later on we are going to consider a mathematical equation also. Here we are going to, I have very clearly mentioned, bond model is qualitative analysis, means how the things are going to be is going to explain with the qualitative analysis. Quantitative analysis, the same thing what we have discussed, but we need to represent with the math also. Okay, so please concentrate. Okay, now suppose what we are discussing is the intrinsic semiconductor now. Okay, so for an intrinsic semiconductor material, for an intrinsic semiconductor, okay, the number of electrons n must be equal to number of holes must be equal to ni. Okay, try to understand the representation. Small n we are using for number of or concentration of electrons, I can say, per unit volume. Okay, P is what? Concentration of holes. Ni is what? Intrinsic concentration or intrinsic carrier concentration. Okay, so what is Ni here? Is very important parameter. Intrinsic carrier concentration, or simply intrinsic concentration, you can say. Okay, and anyhow per centimeter cube or per meter cube, that is per unit volume you are going to consider. These are the units. Okay, now we'll see how we can get this value of n and p. Okay, or how many are going to be present. Okay, so we know that there are 4 different particles that are going to be present in the semiconductor material we have given. So what they are? The different particles are the different particles are, so what they are, starting with phonons, photons. Okay, now free electron, I am simply writing it as electron, please. Okay, electrons and holes. Okay, hope I am clear. Yes. Now, if you consider the average energy of the particle, okay, any one particle means any one of these four. Okay, we can give that value as, okay, let me write here, the average energy of each particle K into T. Okay, please remember this. Okay, the average energy. Okay, so the average energy, I'm sorry, average energy of each particle. Here it should be energy. Average energy, okay, of each particle is going to be how much? It is K into T. So you know what is T? It is the absolute, temperature. And what is the K here? What is K here? This is Boltzmann constant. It is called Boltzmann's constant. Okay, so the value of K is given by K is equal to 8.62 into 10 power minus 5 electron volts per degree Kelvin, or simply Kelvin. Okay, and you know what is 1 electron volt is equal to? Okay, that is 1.6 into 10 power minus 19 joules. You can convert this also into that. Then K bar is going to be equal to 1.381 into 10 power minus 23 joule per degree Kelvin. Okay, so where K is the Boltzmann constant, this is the numerical value of it. Okay, including your units also. Okay, now let us consider at room temperature. Okay, at T is equal to 300 Kelvin. Okay, you can put the value of T and K here. You can get it. This value will be KT is equal to 0.026 electron volts. Okay, please, these are the standard values. Better it is remember these values. Okay, KT is equal to how much? 0.026 electron volts. Okay, yeah, in some textbooks, okay, it may vary, little bit difference will be there, but anyhow in the problems usually they are going to mention the values. If they have not mentioned, you can take this default. What is the KT value? 0.026 electron volts. Hope I am clear. Yes. Okay, so these are the standard values, please remember. So what is this KT? We have taken the average energy of the particle. Okay, and here one more important point that you must understand here is almost all the parameters that we are going to consider for the semiconductor material are going to be what? Average values, not the absolute value. Okay, yeah. Now let us go further. Okay, now the particles which are going to be present, or I can say in the correspondingly there are traveling waves. No, these are going to move within the crystal. Yes sir. Okay, particles are going to converging to a particular point. Otherwise, what I can say, the waves are going to interfere, and if they interfere, and the energy of these particles is going to be equal to, at least equal to, okay, bond strength, covalent bond strength, what will happen? The covalent bond is going to be broken, releases an electron, and there is a vacancy. That vacancy you will call it as the hole. There is nothing but I can say electron hole pair is going to be generated. Am I clear? Okay, now we must identify here how many number of particles has to converge to break a covalent bond. Is my point clear? Yes, we know what is the average energy of the each particle. Now what I want, how many number of particles are required to break a covalent bond. That is what we need to find it now. Okay. Okay, it's a very simple way that I'm considering here. Okay, if you know the simple mathematics, okay, simple concepts, you can easily understand these things. Okay, now what we need to try to do here is, I'm considering, okay, for example, I'm taking silicon material. You can take the germanium also. Okay, consider silicon. Okay, now default it is at the room temperature. What is the energy gap now? Energy gap of silicon, it is 1.1 electron volts. Okay, then the average energy of each particle, the average energy of particle, okay, is equal to how much? KT, that we got it as 0.026 electron volts. Okay, now the number of particles required is, it's a simple, you know, mathematical relation I'm writing. Okay, number of particles required to break a covalent bond. How much? Yes, each particle is having how much energy? KT. What is the bond strength? Is Eg. Okay, yeah, here better talking about the bond. No, we'll continue with the same. Okay, so what I can say here, silicon bond strength, I can say silicon bond strength, silicon bond strength. Okay, how much it is? 1.1 electrons, because still we don't know what is the band and all. Okay, let's try to stick to this one. Okay, later on we'll talk about that also. Okay, so silicon bond strength is how much? 1.1. Now what is the formula that I can write here? Yes, it is nothing but what? Silicon bond strength divided by the average energy of the particle, I can say. Yes, so silicon bond strength. Yeah, here I have taken example for silicon, or simply you can write it as what? Bond strength divided by average energy of the particle. Average energy of the particle. Okay, so yeah, please don't try to, you know, by heart any mathematical equation or any expression that we are going to get. Try to understand, you can easily remember them. Okay, and that is the reason why I'm explaining each and every step. Okay, there are no assumptions. Okay, maybe there will be few assumptions which we are not requiring, but in the conceptual part, almost all we need to understand why this term is present in that equation. Okay, so it is very logical that what is the expression that I have written. There is no, you know, meaning of by hearting that equation. Fine. Okay, so simply what I am going to get now, this is equal to silicon bond strength is how much? 1.1 electron volts divided 0.026 electron volts. Hope I am clear. Yes, so calculate this value. Please calculate this value. So this will give how much? Approximately 42, approximately 41 point something you are going to get. Let us round it off. It is what? 42. So what is the meaning of this? What is the meaning of this? If 42 particles are converging to a particular point, then a covalent bond is going to be broken and it releases the electron hole pair. Now we can very clearly observe that this cannot happen at every point in the crystal structure. Am I correct? Yes, sir. Obviously this cannot happen at every point, in the crystal structure. Yes or no? Because 42 particles has to converge. It's not the simple thing. Okay. So we'll see why it is not the simple thing. Okay. Now let P is the probability. Okay. Let P is the probability that a particle is going to collide. Nothing but converging. Okay. Is the probability that a particle is going to collide. Okay, so since it is probability, we can very clearly see P will be less than 1. Yes or no? Probability at most it's going to be 1. Anyhow, we can take it as 1. Okay. Now, if collisions of different particles, we can consider them as what? Independent events. Okay. Obviously, yes. So the collision of different particles, different particles is going to be what? Independent events. Okay. The collision of different particles is going to be independent events. Okay. Try to concentrate this point. This is very important one. The collision of different particles is going to be what? Independent events. Then what will be the total probability that 42 particles are going to collide or converge? Yes. The total probability that 42 particles, okay, 42 particles are converging, or you can say colliding. Okay, converging. How much? It's going to be P into and so on. 42 times you have to write, which is nothing but P power 42. Hope I am clear. Yes. Okay, so you can see P itself is less than 1. Now it is raised to the power 42. You can imagine what will be the probability. And that is the reason why the statement that we have given here, okay, you can understand. Okay, so please try to concentrate. Okay, these points are very important. Okay, and whatever here we have given, the mathematically, that is what we have concluded earlier itself. Obviously, this cannot happen at every point in the crystal structure. Why? You can see, if you want to make 42 particles to converge, what is the probability? It is P power 42. Hope I am clear. Yes. Now, let us consider the intrinsic concentration. We know for silicon and germanium, these are the standard values. Again, you can remember them. Okay. From that, we can give some, we can get some mathematical equation also. Yeah, hope I am clear with whatever the explanation that I have given now. Okay. Now let us consider the intrinsic concentration. Okay. Ni value. Ni. If you consider for silicon, okay. Okay, no problem. Silicon, this Ni is going to be equal to 1.5 into 10 power 10 per centimeter cube. Please try to remember these standard values. Anyhow, in the problem they are going to mention, but if you remember these values, okay, some of the concepts is going to be easy for you to understand. Okay, and if you go for germanium material, this Ni will be, it is 2.5 into 10 power 10 per centimeter cube. Okay, and the atomic density, if you consider, okay, atomic density, if you consider silicon, its value is 5 into 10 power 22 per centimeter cube, and for germanium this value is 4.42 into 10 power 22 per centimeter cube. So what is the meaning of this atomic density? In a per centimeter cube volume, these many number of silicon atoms are going to be present. How many? 5 into 10 power 22. In case of germanium, it is 4.42 into 10 power 22 or 4.421 also they will write in some textbooks. Hope I am clear. Yes. And these are the intrinsic carrier concentration. These are the standard values. Please try to remember them. Okay. Now we are dealing with the what? Silicon material. Now let us continue with the same example. Okay. Now let Ni, okay, for silicon, I'm considering for silicon approximately equal to, I'm neglecting that 0.5 for simplicity, 10 power 10 per centimeter cube. Please try to understand whatever this part we are going to have. From that we can, okay, am I clear? Okay, now can I write whatever p power 42 I have, p power 42 is equal to how much? Can I say 10 power 10, because this is the Ni value, divided by per unit volume I have 5 into 10 power 22. So this is equal to 1 divided by 5 into 10 power 12. Okay. Hope I am clear. It is 1 divided by 5 into 10 power 12. So what is the meaning of this? What is the meaning of, okay, mathematically it's okay. Physically what it is going to represent, try to understand. Yes. What this 1 divided by 5 into 10 power 12 is going to represent? It is going to represent out of 5 into 10 power 12 atoms, okay, only one is going to contribute for the generation of electron hole pairs. How many? 5 into 10 power 22. But out of 5 into 10 power 12 silicon atoms, only one atom is contributing for the electron hole pair generation. That is the physical meaning of this equation. I'll repeat this point again. Okay. If you remember here, we got the total probabilities how much? P power 42. So now we know anyhow the value of Ni here. Okay. Now this 0.5 I'm neglecting, so I'm taking 10 power 10 per centimeter. If you want, you can take 1.5 also. There is no issue. Okay. 10 power 10 per centimeter cube. Now can I write P power 42 like this, which is 10 power 10, which is Ni actually. And how many number of atoms are present per unit volume? These many. That is what. Okay. So let me write this in the statement form. Okay. So this means it represents, or I can say it represents. Okay. Only one atom is going to contribute. Okay. In electron hole pair generation out of 5 into 10 power 12. Okay. Am I clear? Okay. So it represents one atom is contributing in electron hole pair generation out of 5 into 10 power 12 atoms. Anyhow, per unit volume you are taking, please keep it in mind. Okay. At this point, you must understand why there is a carrier concentration is less in case of semiconductor compared to the conductor or metal. If you remember, okay, for a conductor, each atom is going to contribute at least one electron. But what about semiconductor material? That number is going to be very, very less. Hope I am clear. Okay. So let me write that point. This point you need to, understand. Let us take it as node. So what it is? The free electron concentration or hole concentration, the free electron concentration. Please try to understand and take down. Okay. Electron concentration and hole concentration. Okay, let us consider at room temperature default. At room temperature, at room temperature is a very small fraction, is a very small fraction. Okay, compared to what fraction? If I say it's going to be with respect to some parameter, no, fraction, okay, of the concentration of the concentration of silicon atoms, concentration of silicon atoms. Seen out of 5 into 10 power 12, only one atom is contributing. Okay, okay, silicon atoms. So this is, okay, very much unlike in case of conductor. This is very much unlike, okay, in a conductor, or you can also call it as what, metal. Okay, so in case of metal, each atom is going to contribute at least one electron, nothing but the charge carrier. But so let me write that in a metal, every atom, okay, every atom, okay, every atom contributes to okay, what contributes to a current carrier or charge, a current carrier. Hope I am clear. Yes, are you understanding? In case of semiconductor material, very small fraction of atoms are contributing for the current carriers, but in case of metal or conductor, you can very clearly see each atom is going to contribute, and this is the reason why the carrier concentration is going to be very high in case of conductor and it is less in case of semiconductor material. Hope I am clear with, okay, whatever I've written. Okay, please, this point is very important to understand. Okay, now let us consider, this equation what we have written here. Okay, this one, silicon bond strength divided by the average energy of the particle. No, suppose if you increase the temperature, what will happen? I'll just briefly explain this. If you increase the temperature, what will happen? The average energy of the particle is going to increase, no? Yes. On the other hand, anyhow, even the bond strength also decreases. Let us take now for the constant. Now the average energy of the particle is increasing. If average energy of the particle increases, what will happen? The number of particles that are required is going to decrease. Yes. And if this number of particles are decreasing, what will happen to this value now? The intrinsic concentration, this is going to increase. So in that way you can find out. Are you understanding? Okay. So this is going to decrease now. If P power, no, instead of 42, it is going to be less than 42. Okay. So then what will happen? This value has to increase now. So what is the meaning of that? More and more number of atoms are going to involve in the generation of electron hole pairs, which makes the carrier concentration to increase. Okay. So this is, qualitatively what it is going to be now. Okay. Now, from this discussion, what we made, we can write some, important mathematical relation. Okay. From whatever the P power 42 that we have written, no, from this we can try to understand this. Okay. Can I say now, Ni is equal to capital N. Yeah, I'll define the terms. Let me write first. Ni is N into E power, okay, E divided by KT. I'm sorry, not E. It is P. I'm sorry. P power E by KT. Let me define each term here. Okay. What is N? Intrinsic concentration. Intrinsic concentration. What is this capital N? It is atomic density. is nothing but what? Atomic density. What is this capital E? Sun. Bond strength. What is this kT? Average energy of the particle. Please try to understand average energy of the particle. Yes, sir. And what is this P? Probability that a particle collides. Sir, probability that a particle collides. Yes. If you see this equation from this only I have written it. What is 10 power 10 actually? Ni. What is this 5 into 10 power 22? It is nothing but capital N. Anyhow, P is there. How you got this 42? Where from you got 42? This one. This is E. Okay. And this is KT. Okay. So this is nothing but we have taken E divided by KT. Okay. Hope I am clear. Yes. Now what is this E by KT? I can say. What is E by KT? E by KT is the number of particles that are required to break a covalent bond. To break a covalent bond. Okay. So hope I am clear. Okay. Now from this also you can very clearly see as you increase the temperature, what will happen? As you increase the temperature, what will happen? We can from this equation also we can very clearly see that this Ni is going to increase. How mathematically we'll see it later. We can very clearly see from this also. Okay, this T is increasing. Okay, anyhow E we take it as for time being constant, then this is going to decrease. Yes. Okay, so in this way you can understand it. Okay, now again this equation I'll just rearrange so that we can have one more important relation. Just I'm rearranging. You see that what we got? Ni is equal to capital N is there, no? Capital N. Instead of P, I'll write 1 by P. Power minus E by KT. Minus E by KT. Okay. Now take logarithm on both sides. Log of Ni is equal to what? It is log N. Okay. Natural logarithm or ln you can write, no problem. Okay. Minus. Okay. E by KT. Okay. E by KT. Ln of 1 by P or log of 1 by. Okay. Anyhow, this capital N is going to be constant. Okay. Then we can very clearly see from this log of Ni will be proportional to what? Minus E by KT. Okay. Log of Ni is proportional to what? Minus E by KT. Okay. Hope I am clear. Same from this one only. Instead of P, I am writing 1 by P and putting the minus sign and just rearranging the terms. Then I'll get this. Okay. So here also you can see very clearly as the temperature is going to increase, Ni also increases. Okay. Anyhow, this whatever the discussion that we are making here in detail, again we are going to consider because we need to derive the expression for N. Don't bother too much about of this. Okay, but you must understand how you are getting this equation. Okay, and how electron hole pairs are going to be generated in the crystal structure. This is important one. Okay, how you are generating our concentration of electrons and holes that we are going to get. Okay, so this process is going to be very important. Yes, hope I am clear with whatever the discussion that I made now. Okay, now so with this the first part. Okay, I can say in the intrinsic semiconductor nothing but bond model. Second part in the intrinsic semiconductor, what is that? Bond model is completed. Okay, now we'll go for energy band model. Okay, fine. Let us consider next. Okay, what we are going to consider here, energy band model, okay, or simply I can call band model, okay. You can drop that word energy. Hope I am clear. Yes, okay. So bond, we are going forward next, which is energy band model or band model, okay. Yeah, this is very important, okay. And in the beginning, at the first topic itself, we are going to form the energy band diagram. How we are going to get, we are going to discuss. So pay attention, okay. Please, again I'm mentioning, whatever the bond model and band model we are discussing for the intrinsic semiconductor material, with little modifications we can do for the extrinsic. Again, there in the extrinsic semiconductor material, I'm not going to spend this much of time, and that is the reason why I'm spending a lot of time to explain these things, okay. So please try to understand this point. Please concentrate. The similar type of analysis we are going to do bond model and band model in case of extrinsic. Whatever the discussion that we are making here, I'll take from this, okay. Don't expect again there each and every point that I'm going to explain, okay. Yeah, hope I am clear. Yes. Now let us consider what are the basic principles, okay. The basic principles of band model are, okay, there are three basic principles. Anyhow, these things you know very well. You might have studied in +1 and +2, but here with little modifications we'll try to adapt for our discussion, okay. So let us consider one by one. We'll see what they are, and then in detail we need to discuss these things, okay. Let us take the first one, okay. The first one is going to be called as allowed states. What it is? We are calling it as what it is? Allowed states. So what is the meaning of this allowed states? You know very clearly that the electrons are going to occupy, are allowed only in certain energy levels, okay. Electron cannot be present everywhere where you want, okay. There will be certain energy levels, okay, or energy states where the electron can occupy that particular energy level, okay. So in this one again you can have some sub points, okay. The first one is only certain energy levels are allowed. Only certain energy levels or states, interchangeably you can write, levels are allowed. That is what I explained, okay. Your electron can occupy certain energy levels only, okay. We'll see where it is going to be, okay. Then we know very clearly that the electron is going to occupy the lowest possible energy first, go to the next energy level, higher energy level, okay. So let me write that point. Electrons occupy the lowest energy level or state, lowest energy states available. Yes, yes or no? And we know very clearly from the Pauli's exclusion principle, no two electrons occupy the same energy state or same energy level. No two electrons occupy the same energy state. Yeah, please. These things may not be the new things, okay, but try to understand them. We'll later on, okay, we'll try to adapt these things to our discussion, okay. So the first principle is what? Allowed states. In that, what you might, only certain energy levels or energy states are going to be allowed where electron can occupy. The second one is what? The lowest possible energy levels will be occupied by the electron first, and then it goes for the higher energies. Third one is what? no two electrons occupy the same energy state. Okay, hope I am clear. Now, the second principle of the band model is going to be, now we have seen there are only certain energy levels where electron can present. Now, how they are distributed over the energy we must understand. Okay, how these energy states or energy levels are distributed over the energy, that you must understand. That is the second principle. Okay, so can I write it as distribution of allowed states? Please try to follow the notations or the terminology that we are giving. Okay, distribution of energy states, distribution of energy states over energy. So this is usually represented with n of e. Okay, what is it? N of e, which is called as density of states function. Okay, in detail we'll discuss later. Let us find it. Okay, this is the notation that we'll follow. What is it? N in brackets capital E. E is the energy here. Okay, so it is distribution of energy states over energy. Hope I am clear. Let us consider the third principle. Now, first one is what? Try to think in the logical way. First one is the how many number of energy states are present. Second, how they are distributed over the energy. Now, what you need to find out? How many are occupied? Okay, or how many are occupied by the electron? That you must understand. Okay, that you must get it finally. Okay, so can I say the fraction of occupied states? I can say fraction of occupied states. Okay, fraction of occupied states. Okay, and at a given, it is important. Okay, at a given energy level E and temperature T, because this also, if you change the energy or if you change the temperature, this is going to change. Hope I am clear. Yes, let me go through allowed states. Second, distribution of allowed states. Third, out of this, how many are occupied? Nothing but the fraction of occupied states. Here we are specifying the energy and the temperature. Yeah, similar type of things. Again, we are going to discuss in case of extrinsic semiconductor. Please concentrate. These things are going to be very important. Okay, don't think that these are not required. If you understand these things, you can easily understand the other topics. Okay, hope I am clear. Now, let us start with the first principle. What it is? Allowed states. So we'll see one by one. Okay, let us consider the first one. What it is? Allowed states. Okay, so here in this one we are going to draw the how the energy band is going to form. Okay, so please try to concentrate, try to understand this point. Okay, this is very critical and very important one for you. Okay, yes. Okay, now again let us consider the silicon atom itself. Okay, with the silicon I will continue. So what I am going to consider is okay, silicon. Okay, which is, there are n atoms that are going to be present. Consider silicon with n atoms. Okay, or n atom system I can call n with n atom system, n atoms system. Okay, or simply I can say consider n atom system. From that we can take it as silicon. Okay, consider n atoms system. For example, silicon. Now, what is the atomic number of silicon? Please, what is the atomic number of silicon? Atomic number. It is 14. Yes, sir. So write the electronic configuration for this. It is 1s2, 2s2, 2p6. Okay. Then 3s2, 3p2. So you can very clearly see that there are 4 valence electrons that are going to be present here, and that is the reason why it is a 4th group element. 3s2 3p2, total 4 valence electrons are going to be present. Yes, am I clear? Now initially we'll start with an isolated silicon atom, then we'll go for n isolated silicon atoms, and then I'm going to form a system. System is nothing but you need to get these atoms close and form a crystal structure. Okay, hope I am clear. First I will start with what? Isolated silicon atom, then n isolated silicon atoms, and in the third step I'll form a crystal structure. Nothing but you are bringing these n isolated atoms close, and then you are forming the crystal structure. So we'll see how the energy levels are going to be get affected. Hope I am clear with whatever the explanation that I have given now. Okay, so let us consider now. Okay, I'm consider isolated, okay, silicon atom. What it is? Isolated silicon atom. Okay, so now we can see very clearly 1s is the first orbit energy level that I can represent, then 2s 2p, then 3s 3p. Okay, so let me indicate that first, and then we'll go for analysis. So let me take, this is what? 1s. Okay, then this is 2s 2p. Okay, then I can have 3s 3p. Okay, 3s. Hope I am clear. Okay, now in 1s how many number of states are present? It is very clearly seen here. 2 states are going to be available. In s orbital 2 states at 2 energy levels will be present. In p orbital it is 6. Okay, now let us indicate that with some notation. So I'll put a circle here which indicates how many number of available states are present. Yeah, please try to follow this notation. Again, here there are 2, here 6, 1 2 3 4 5 6. It is s orbital 2. Again here 6, 1 2 3 4 5 6. Am I clear? Yes. Yeah, please, when you are writing in the notes, this is the first diagram that should present. Okay, now so try to understand this notation. What is this circle represents? Available states, I can call simply. What it is? Available states. Then I'll indicate with, I'll put a cross mark inside the circle which indicates that particular state is occupied by the electron. So can I say occupied state? Occupied state. Okay, or occupied states. Is it fine? Now in the 1s we can see 1s2 means what? 2 electrons are present, so both are occupied. Here also both are occupied. Here 2p6, so all the 6 are occupied. What about here? Both the orbits are occupied. But in case of 3p there are only 2 electrons. So randomly you can select 2 states are going to be occupied with the electron. Hope I am clear. Okay, so here in 1s how many number of states are present? How many number of states? 2 states, and both are occupied. 2s also the same thing. But p orbital 2p there are 6. What about 3s? 2 states, 2 are occupied. What about 3p? It is also 6, but only 2 states are occupied. Okay, now please try to understand here what is the y-axis here. What is the y-axis? It is always, I already mentioned, it is electron energy. Electron energy, E. Yes. Now the same thing, okay, the same type of representation I'll do for n isolated silicon atoms. Are you understanding? N isolated silicon atoms now I am going to consider. Please try to concentrate. This is the second diagram that must be present in your notes. Okay. Now what I am considering? N isolated silicon atoms. Okay. So let me represent the orbits first. So this is what? 1s. Okay. This is 2s, 2p, 3s, 3p. This is 3s. This is 3p. Okay. Now how many are there? N isolated atoms. Okay. Now can I first represent? Okay. How many are here? Okay. Let me first put the number of states, and then we will go for how many are occupied. Okay. 2, 6. Is it fine? Okay. Now tell me how many states are present for 1s now? How many states are present for 1s? It is 2n states. Am I correct? Here 2n states. What about here? Let me write here 6n states. What about here? 2n states. 6n states. Yeah, please try to understand. Okay, this is the second diagram that you must draw. Okay, 6n states. Now, how many are occupied here? All are occupied, no? Here also. Here all are occupied. Here also. But in case of this only 2, let me represent with the same. Okay, these are occupied. Now, how many number of electrons are going to be present here? I have 2n electrons here, 2n electrons here, 6n electrons here, 2n electrons, and what about this? Only 2n electrons. Hope I am clear. Yes. What I am considering here, n isolated atoms. Again, this is going to be electron energy E y-axis. Yes. Okay. Hope I am clear till now what I have represented. Okay. Now, what I am going to do is, okay, what I am going to do is, now I am going to start reducing the distance between the atoms. Please try to concentrate. I am going to now decrease the distance between the what? Atoms. Now what will happen? When you are keep on decreasing, you can say at a particular distance, the out electrons will start interacting with each other. What are the outermost orbits here? This 3p, 3s and 3p. They are going to start interacting with the other, outermost orbit electrons. Hope I am clear. Okay. Now let me represent. Okay. So here, what I am going to consider is, this is electron energy. It is the default thing. Okay. Yeah. Try to understand what I am giving here. It is very important for you. Okay. And what I am taking on the x-axis is the, I can say, atomic distance or interatomic distance or atomic separation also you can say. Okay. Now, let me represent. This is 1s, 2s, 2p, 3s, 3p. Okay. 1s, 2s, 2p, 3s, 3p. So this should be the third diagram. Please, you can listen. I'll give time to write. Please listen first. Try to concentrate. Okay. Now, here, how many states are present? 2n, because n I am considering, no? So here 2n states are present, 2n are occupied. Here also 2n states are present, 2n are occupied. Here 6n are present and all are occupied. Am I correct? And here 2n are present, 2n are occupied. But what about this? 6n are present, but only 2n are occupied. Okay. Let me write that also. This is 2n states, 2n electrons. Okay. Here 2n states, 2n electrons. What about here? 6n states, 6n electrons. Here 2n states, 2n electrons. Here 6n states, but only 2n electrons. Hope I am clear. The previous diagram that what I have represented here, I'm now I start slowly decreasing the distance between the atoms. Now what will happen according to the Pauli's exclusion principle? Okay, let me write that point and then we'll go for the diagram. Okay, as the separation between the atoms is reduced or decreased, okay, the interaction among the various atoms is going to start. Okay, and according to Pauli's exclusion principle, no two electrons can have the same energy, okay, or they cannot occupy the same energy state. Both will be the same. Okay, hope I am clear with what I have written now. Yes. Yes. Okay. Now, if that is the case, try to understand this how it is going to change. Okay. So as you are decreasing the interatom, okay, first the outermost orbits are going to get affected. They are going to start interacting with the nearby outermost orbits of the other atoms, obviously. Okay, and if you further decrease, then the next level and next level, like that. Okay, so the first sorry, the first affected is going to be what? 3p3s. Now what will happen is, according to this one, no two electrons can have the same energy. No, because of that, what will happen is okay, so this energy level is going to start splitting into energy levels. Okay, discrete energy levels, like this. It's like this. It starts splitting into the level, because no two electrons should have the same energy. Hope I am clear. Okay, so if you further keep on decreasing, you may observe this type of structure. Okay, you may observe the band structure is going to be something like this. Okay, Okay, so it looks something like this you are going to get. Okay, now try to understand what these points are going to represent. Okay, try to understand. Let me indicate some, now let us consider this point, this one. Here how many states are going to be present, and here how many number of states are going to be present, and how many number of electrons. Please try to concentrate, this is very important one. How many number of states are there here? 2n states. And how many number of electrons? 2n electrons here. What about here? It is 6n states. And how many electrons? Only 2n electrons. Yes. Now after this, how many number of states and electrons are going to be present here? How many? Now total 6n plus 2n, 8n states. It is 8n states. And how many number of electrons? 4n electrons. Hope I am clear? Yes. Now, if you further decrease, okay, this is the y-axis is what? Atomic distance. No, you are moving left. Means what? You are decreasing the interatomic distance or distance between the atoms. Okay. And if you consider that, okay, let us take, this is the interatomic distance in a particular semiconductor material. Okay. Okay. This is the interatomic distance in a particular semiconductor material. Then what will happen? We'll see. Yes. Okay. Now, if you consider here, how many states are going to be present here, and how many states are going to be same 8n now will be divided into 4n and 4n. Hope I am clear. How many are going to be present is 4n and 4n. The total 8n are there. They will be divided. One is going to be 8n states. The other one is going to be another 8n, 4n states. Okay. Now, let me write that also. Here, if you consider this, how many states are present? 4n states. How many electrons? We'll see it later. Okay. And similarly, how many states are going to be present here? How many? 4n states. Yes? Yes or no? And now this you can take it as energy gap actually. Okay? Whatever this we are having, this can be considered as what? Energy gap, where there are no allowed energy levels. We will call it as what? Forbidden band or energy gap. Hope I am clear. Yes. Okay. Now tell me, how many number of electrons will be present here? 4n states in this one, in this lower one, and how many number of electrons are going to be present in this upper band? Yes. If you see the principles that we have given, the first principle is what? Allowed states. In that we have given these three statements again, or these are the characteristics. Only certain energy levels are allowed. So you can see very clearly in this one. Okay, in this one, here there are no allowed energy levels within the energy gap. Here it is allowed, and the above it is allowed. Okay, and electrons occupy the lowest energy level that are going to be possible first. So we can very clearly see, out of 4n electrons, all the 4n electrons will be occupied here. And what about here? 0 electrons. Okay, so this we'll call it as the valence band, and this we'll call it as conduction band. Okay, this is called as what? Valence band, and this is called as what? Conduction band. Now we can very clearly see that the valence band is completely filled, the conduction band is completely empty. Are you getting? Okay. Now actually what is this point is crystal separation, I can call this one. What it is? Crystal separation. Yeah, there is one important point you must understand here, crystal separation. Okay. Suppose you consider a metal. Okay. If you consider a metal. Okay. the interatomic distance or separation of in the crystal is going to be present within this range. Okay, this point is very important, right, to understand. If I consider this range, okay, I'll write here in a metal, in a metal, the crystal separation, the crystal separation lies within this range, within this range. So please try to understand this one. Okay. So if you see here, the green line dotted lines I have given, no, green dotted lines between the green dotted lines. If you observe, can you separate the conduction band and valence band? No. And if you remember the day one that we started with the energy band diagram representation, we have very clearly given that there is an overlap of conduction band and valence band. The reason is this one. But if you go for semiconductor materials, the crystal separation is not going to lie within this range. It may be, okay, further it is going to decrease, and the crystal, the band structure is going to be like this, something like this. So we are going to get energy band diagram in this way. Okay, we'll see what factor is going to decide crystal structure. I'll give just a statement. Okay, hope I am clear. Given now, this diagram is very important one. Try to understand. Okay. Now, if you further keep on decreasing the interatomic distance, what will happen? The next level, next energy levels, what they are, 2p 2s are there, no, they are going to start interacting. Okay, so if that is the case, okay, if that is the case, maybe somewhere here they are going to start interacting, and the energy levels are going to start splitting in this way. And if you further keep on decreasing, then even 1s orbit is going to happen in this way. But anyhow, our interest, okay, because you are not going to keep on decreasing the distance, whatever we have given here, this part is going to happen. Hope I am clear. Now we'll see what factor is going to be influenced by the or decided by the interatomic distance. Let me write that point first and I will explain. Okay. Okay, so let me write. Yeah, you can take simultaneously. One thing, those who have not written this diagram, please take it. I'll give 2 minutes of time. Please complete it. Okay. So this is very important one. Please, you have to draw this. Okay. Try to understand and draw it. Make it fast. I'll give 2 minutes. Make it fast, and then we'll go for the further discussion. Okay, so this is, you can call it as crystal separation, atomic separation also you can represent it. Different names. You can also call it as what? Atomic separation. Okay, crystal separation or atomic separation. Okay, now let us define what factors are going to decide by this. Write down that the atomic separation. Okay, the atomic separation in a crystal is decided by the fact that is by the fact that, okay, all the sorry, all the attractive forces and repulsive forces must cancel. Nothing but the system should possess the lowest possible energy. Okay, so this will decide the crystal structure. Okay, so it depends on so many factors. Okay, so fact that what, all the attractive and repulsive forces, repulsive forces, okay, should cancel, should cancel. Nothing but in other way I can call that, that is the system possess the lowest possible energy. Okay, so system possess the lowest total possible energy. Okay, so depending upon this factor will give this, atomic separation or the crystal separation. Okay, and that is the reason why if you observe here we have given this range is going to be for what, within the green dashed lines are there, no, this is going to be for the metal, but semiconductor it's going to be in this way. Okay, so depending upon the material properties this may change now. Okay, because of that energy gap is going to be different. You can very clearly see if you move right or left the energy gap is going to be different. That is why the energy gap is going to be different. Hope I am clear. Yes, yes. Okay, so this is about what, how the allowed states are going to be formed. Okay, so from this we can very clearly see that there is one energy band and another energy band separated by an energy gap or forbidden band. Now let us indicate this, energy band diagram or energy band picture. Anyhow, this in the x-axis, if you see here, and y-axis is always what, electron energy. This is default. Now in this case, you are fixing the atomic separation. You are not changing it now. For a particular crystal, when you form it, this crystal atomic separation is going to be the same. Okay, so now let us draw the energy band diagram and energy band picture at a particular atomic separation. Okay, so try to understand this. So what I am considering here, the energy band picture, energy band picture, energy band picture at a particular atomic separation. Okay, or atomic distance also you can call it. Okay, fine. Now you see here in the diagram that we have represented. Okay, this dashed line I have represented. Now you can see it is intersecting now at different points, 1 2 3 4 5 6 7. So these things you can represent here. Okay, so with a point I can, wherever the intersection is there, I'll put a point. Okay, now let us take this. Okay, I'll use a different color so that it will be clear for you. Okay, now actually this is called as the vacuum level. Let me write, it is nothing but what, vacuum level, and its energy you can write it as E naught, and then we'll give this one. Okay, not this one. Okay, so this dot 1, let me put here this one, 1 2 3 4 5 6 7 total. Okay, am I clear? So let us take, this is 1, 2, 3, 4. Okay, so this is 2s, 2p is over. Like this. Whatever intersection that I have, I'm representing here. So this is called the vacuum level. Okay. Now what is this? This one. What is this? It's nothing but we can call it as the conduction band. What it is? I'll write with different color. What it is? It is conduction band. Okay. And what about this one? Is the valence band. Please try to relate the diagram with what I am writing. And what about this one? What about this one? Is the energy gap. Yes or no? Is nothing but energy gap. Okay. Anyhow, the lower things are not actually essential for us. Okay. We are not going to consider them. Is it fine? Okay. Now, but if I want to represent some information in this, whatever we have represented, it is very difficult for us to represent the information. For that, what we are going to do is, we'll make some little modification for this. Okay. So what we are going to do now with little modification. So corresponding to this, I'm going to write, okay, representation of, okay, representation of band picture. Okay. Or you can say energy band diagram, simply band diagram also, energy band diagram. Okay, hope I am clear. Let me write here itself so that, okay, energy band diagram. So here what I am going to do is, you just, whatever this dot I am having, in place of that, okay, I am going to put a horizontal line, because the information that I want to represent here, any information by using this, diagram. For that, what I'm going to do now is, I'm just putting a horizontal line like this. Okay, hope I am clear. Sorry. Okay, so now this is nothing but what? E naught. You can call it as what? Vacuum level. Okay, and try to represent the other things. This is, I can say, top of the valence band. What it is? ET. Sorry, top of the conduction band. I'm sorry. ET is what? Top of the conduction band. EC is the bottom of the conduction band. Okay. Then EV is the top of the valence band, and this one is bottom of the valence band. So you can very clearly see now, this you can take it as valence band. What about this? Conduction band. Okay. And what about this one? Is the energy gap. Energy gap. Or we can also call it as what? Forbidden band. Because the electrons are not allowed within this energy gap or forbidden band. Hope I am clear. See, actually, this is the representation that we got. Okay, but if I want to represent every time this, it's going to be difficult. For that, what we are doing at a particular, atomic separation or atomic distance, you have to represent. So if I want to represent like this, I'll get like this. But we cannot get any information from this. For our representation convenience, I am putting like this. Okay. Now, what is the wire? let me write here. What is the y-axis? What is the y-axis? Always it is electron energy in both the diagrams. Y-axis is electron energy, it is default. Then what about x-axis? For this particular diagram I am asking, what is the x-axis? Here there is no meaning of talking about the x-axis because I am considering this diagram at a particular atomic separation. It is fixed. But for our convenience, we are representing in this way. Hope I am clear. Okay. Now let me represent this. You can also take it as what Eg, energy gap is represented with Eg. And what is this difference? Usually we'll call this one EC to E naught, vacuum level, is represented with Q into chi, that is electron affinity. What it is? I think you might have known all these things already. Okay, you might have studied in your +1 and +2. I'm just giving. Okay, it is electron affinity. Okay, so Q into chi, the difference between vacuum level and EC. Okay, so actually this is how usually we are going to represent the energy band diagram. Actually we got from this, step by step we have taken, from that we are representing for our convenience like this. So please remember, when you are drawing the energy band diagram for a particular crystal, the x-axis represents what? The atomic distance. It is fixed and there is no meaning of talking about the x-axis. But when you go for the device and you are drawing the energy band diagram, then definitely the x-axis is going to represent the distance. But for this diagram what I have drawn now, okay, there is no meaning of talking about the x-axis. Anyhow, y-axis default is what? Electron energy. Okay, so hope I am clear with whatever we have given now. Okay, yes. So with this, the first principle is completed. What is that? Allowed states. Okay, now quickly we'll go for the doubt clarification for another 15 minutes. Okay, please, those who got clarified their doubts, okay, please down your hands and unmute your voice. Okay, and one more important thing, those who are asking the doubt, please ensure that there is no disturbance surrounding you. Okay, disturbance that is present, because I am getting lot of in the other people are shouting behind you. Okay, so it creates lot of disturbance. Okay, you need to give respect to the time of others. Okay, so this is my request. Okay, yeah, we'll see one by one. Okay, so please make it fast. And one more important thing that I want to mention here, see, doubt clarification is, see, most of the doubt, this point already I mentioned, most of the doubts, if you go and read for the second time or the third time, okay, more than 60% doubts will be get clarified or on your own itself. And if you discuss it with your friends, and another 30% doubts will be clarified. Only for 5 to 10% you require the assistance. Okay, but anyhow I'll clarify, there is no doubt. But if you have some doubt and just you are posting and asking someone and get clarified, you will forget there itself. If you spend some time, then easily you can remember. Okay, you will never forget this one. Okay, so in two cases you don't get the doubts. One, if you understood everything. Second possibility, if you don't understand anything also, you don't get the doubts. So hope both are not possible. Okay, it's the ideal case. Okay, so I'm not a bad teacher so that you don't understand anything. Okay, so in that way I'm not going to be 100% that I can give. Okay, but okay, so keep it in mind and try to ask the doubts. Okay, yeah, Gudur 145047. Yeah, please go ahead.
Hello, good morning, sir.
Very good morning.
Sir, page number 29F.
Page number 29F. Yeah. Please. Please ask your doubt.
Sir, these electrons, free electrons, will go to bounded electrons or holes in Auger recombination, non-radiative recombination?
No, I'm not understanding your doubt.
These free electrons will recombine, no, sir?
Yes.
Then they will go to free bounded electrons, or again they will go to free.
How it will go to bounded electron? Please tell me how it will go.
Oh, again they will act as free electrons.
No. See, your question itself, there is no clarity.
You
If
said
you
no,
take,
sir. When the free electrons are recombined, then they will go to either electrons or holes.
it will not go, man. I have very clearly mentioned the energy is going to be transferred to electron or hole. Please be careful when you are using the words. I didn't say that it's going to be. No, the
Yes,
energy will be transferred.
Yes, sir.
Is it fine?
Sir, another doubt, sir. Sir, the particles will produce traveling waves, sir. Then two particles traveling waves will combine with each other,
Two traveling waves.
interfere with each other, and they will break the bonds, sir.
Not two. That is what we have given now. We have calculated 42 particles has to converge to break a covalent bond. In silicon I have taken. If you take some other material, energy gap will be different. That number will be different.
Yeah, yes, sir. Sir,
Okay.
if temperature will increase, this means concentration will increases, sir.
Obviously.
Then why to doping required, sir? If we just increase the temperature and then we
How much you
increase
can
the
get?
concentration of
How much you can get? How much you can get? That is important, no?
yes, sir.
How far you can increase? That is also important, no?
Okay, if we
Yeah.
increase more temperature, means the device
Yeah.
will be breakdown.
Yes, yes. There are
So
other factors also you need to consider. So
okay, sir.
up to some extent, it completely.
Okay, so up to some extent we will increase the temperature too.
Yeah.
Okay, sir. Thank you, sir.
There is a limitation for temperature also.
Okay, sir. Thank you, sir.
Fine. Yeah, good. Anwar, please go ahead. Anwar. 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 Divyagna.
Good afternoon, sir. Can you hear me?
Yeah. Go
Sir,
ahead.
I have a doubt regarding previous class, sir.
Okay.
Sir, in equilibrium, the first statement was external temperature excitation it can be there.
No, only temperature has to be there. Other than temperature, there is no excitation. Please read
That is
carefully.
that is because it's an ambient condition.
No, obviously, no. You cannot. Sorry, you cannot have. You go anywhere. Can you separate from temperature? Can you isolate?
Yes, sir. Exactly. Like similarly, we can say that illumination also can be part of that. No, sir?
How illumination?
Because anywhere we'll go, we'll have light energy also, no, sir.
Okay, but can it make energy? It can break the covalent bonds and all. It cannot happen, no? Because what is the condition that we have given with the energy of the photon? H nu should be greater than or equal to Eg. So if that condition is not satisfied, there is no breakage of covalent bond.
Okay.
So without light, we cannot survive. Okay.
And sir, one more tiny doubt.
Yeah.
In generally in free electrons, you said that if the particles all converge to a point, that means that say in a crystal there are like 10 electrons dispersed, they all converge to an effective point. Is that what you're saying?
See, if they converge, they cannot stay forever. Okay, it's going to be fraction of seconds. It is going to happen every time. It is going to happen when temperature is.
And in that fraction, the covalent bond breaks.
Yes, and it will scatter. Once suppose 42 particles we have taken. No, now
Yes,
once
sir.
they converge, they are not staying forever there. They will again scatter from that point, and it will continue.
But that energy is used to break it.
Yes, once that 42 particles has been converted and energy is equal, it will break and they will scatter.
Okay, sir. Thank you, sir.
Yeah, okay. Please go ahead. Amit Kumar. Amit Kumar. Amit Kumar, please.
Hello, good morning, sir.
Very good morning.
Sir, I have doubt on a page 41F.
41?
F.
Yeah, please.
So please tell me how can you write this, sir, in 8 n states and 4 n electrons. So please tell me once again time.
How many in the 3p and 3s? How many total number of electrons are present? In 3s, 2n electrons are there. 3p, 2n electrons are there. Total how many?
8.
2n plus 2n, how much, man? 2n plus 2n, what is the value?
So it is 4. Okay, sir. But in crystal separation, sir, how can you write the 4 n state and 4 n electrons?
Okay, I have very clearly mentioned, no? See, this is your first doubt is clarified. You are moving to the second without considering the first. Is your first doubt clarified?
Yes, okay, sir. I understand, sir, ki 8 n states and 4 n electrons.
Now you are asking in the after the
Crystal
formation of the
separation.
4n states or 4n states. You take the allowed states. What is the three first principle we have given? Only certain energy levels are allowed. The second point is what? Electrons occupy the lowest energy states available that are no.
Yes, sir.
Now you see the diagram now. Now total how many total 8n will be divided into 4n and 4n. 8n states. Yes.
Yes, sir. Yes.
Now in the lower energy band, 4n states are there. Higher 4n states. What are the total number of electrons that are present? How many number of electrons? Total number of electrons in the valence band. Sorry, 3p and 3s combinedly 4n.
Yes, sir.
Previously, whatever 8n states and 4n, I am continuing. The 4n electrons, where they are going to present now? Please
Okay,
answer.
sir.
Answer my question. Where they are going to present? Obviously at the lower energy levels only. No, that's why there are 4n states, and in the above state there are 0 electrons.
Yes, okay.
Got it?
Okay, thank you, sir.
Yeah. Varshita, please go ahead.
Hello, sir.
Yeah.
Am
Yes.
I audible?
Yeah, but there is a lot of disturbance. Except your voice, everything I can able to hear.
I have a doubt in 29F, sir.
20?
9F.
9F, okay. Yes, go ahead. Please make it fast.
Can you please explain that impact ionization?
You want to me explain? Or?
Yes, I want to be explained that I didn't understand. In radiated recombination, the light energy will be released.
Come again.
In radiative recombination,
Fine.
the light energy will be radiated, no, sir.
Yes.
In the same way, in impact ionization, what will be released at the output?
What will be the
Going to release at recombination state.
Energy will be released. That can be in the form of heat, and that will be given to either electron or hole. You don't observe any light energy in this case. Yeah. See, I have a lot of disturbance. Okay, I'm lot of disturbance from your side. Please ensure you need to be isolated from other disturbances. Please. Yeah, Venkat.
Thank you, sir.
Venkat, please go ahead.
Hello,
please
sir.
Unmute your voice. Other girl that asked, please unmute your voice. Yeah, previously the girl who asked, please unmute your voice. Yeah, please go ahead, Venkat.
Hello, sir. Good morning, sir.
Good morning.
Sir, in page number 34, sir. 34F.
34F, yeah.
Sir, why we have equated?
Yeah, please go ahead.
Sir, why we have equated to probability, sir? The total 10 power 10 by 5 into 10.
What is it? See, you just think. Please, those who are not asking the doubts, please unmute your voice. I'm requesting your voice, those who are not asking the doubts. Please go ahead. Okay.
Yes, yes, sir.
Mhm.
That P
Yeah,
equal
you
to
you just think on your own. Okay, how many number of charged particles we got total is nothing but the intrinsic constant. Venkat, is this disturbances from your side?
no,
Venkat?
sir. It's not. It's not from my side, sir.
Okay, fine. So this Ni is how much? 1.5 into 10 power 10. No, means these many
Yes, sir.
number of electron and hole pairs are there.
Okay.
Okay. For simplicity, I have ignored 0.5 and taken 10 power 10.
Okay.
Now, how many number of atoms are present? 5 into 10 power 22 per centimeter cube.
22.
Now, so we have very clearly mentioned in the previous, I think, obviously this cannot happen at every point in the crystal structure we have mentioned, no? Because 42 particles has to converge.
Sir,
And
sir.
what is the total probability?
Sir,
P
one
power-
more.
Let me complete, man.
Sir, can you repeat the?
Uh,
I didn't know. I didn't hear, sir. But for from P power 42.
See, 42 particles has been converged. 42 particles are converging, then I'll get the covalent bond to break and electron hole pair is going to be released. Correct?
Okay. Yes.
Yes.
Yes, sir.
Now this at a particular atom it has to happen. At a crystal structure in a particular place it has to happen. Yes or no? So how many atoms are there? Total 5 into 10 power 22. Out of which I got 10 power 10, electron hole pairs. Then what will be the total probability now?
Okay.
Can I say 10 power 10 divided by 5 into 10 power 22?
Yes, sir.
No, that is what I have written.
Sir, in page number 36F, sir.
Hmm.
Sir,
Yeah.
there you said that as T increases, the intrinsic concentration increases, sir.
Yes.
But as T increases, the P power something value will decrease, no, sir.
What is P here?
Probability.
What is the value? What is P? It's going to be what? Less than 1, no?
Less than 1. Yes, sir.
If you are less than value, power is decreasing. The total value will what will happen to the total value? Simple mathematics, man.
Decreases, no, sir. Total.
How it will decrease?
Sir, if 0.25
See,
value.
P power 42, P power 35. Which will be the larger value? P power 42, P power 32.
32, sir.
That is what I have written. That is what I have written.
Okay.
Please spend some time, man. Spend
Yes,
some time. Spend some time. That is what
Sir,
I told very clearly. Yeah.
Okay, sir. No,
Hmm.
clarified, sir.
Okay.
Thank you, sir.
Yes. Swaroop. Swaroop.
Good morning, sir.
Very good morning.
Sir, I have a silly doubt. The relationship that you wrote N is equal to P is equal to Ni.
N is equal to?
P is equal to Ni.
Yeah.
Sir, can you explain that?
What explanation you want there, man?
Sir, what is Ni? I'm getting confused. Either it's whether it is a free electron or a hole.
Both. That's what we have written now mathematically. N equal to P equal to Ni means what? How many number of electrons are there? Same number of holes are there, which is equal. Which we are calling it as the intrinsic concentration.
So there N is equal to the free electron, that intrinsic semiconductor.
I'm not getting.
Sir, in that relationship, N is equal to the number of free electrons in that intrinsic semiconductor.
Yeah, N is free electron constant. That's what I very clearly mentioned. Electron means I'm dropping that word free. Electron concentration means it's a free electron concentration. There is no doubt.
Okay, sir. Sir, and one more doubt in augury recombination. The
How?
energy released, say in augury recombination.
Go ahead.
So in augury recombination, then sir, the energy released is absorbed by which free electrons? Like the free electrons of that same Si atom or
Electron of same Si atom
or
complete
like
your
the
doubt.
neighboring Si atoms.
It may
Like
be
you said,
it can be. See,
so you
this
said
is
that
See, 1 second. Free electron means what? It is not bound
Yes.
to any atom, no? Then you will call it as the free atom.
Yes. Right.
Free electron
Okay,
means it
sir,
is
got
not
it.
bound to any electron. It can move anywhere in the crystal structure. It is not related to any atom now.
Okay, sir.
Got it?
Yes,
Okay.
sir.
Yeah.
Okay, sir. Got it. Yes, sir.
Okay.
Thank you.
Yeah, we'll take a break. We'll meet after 15 minutes. Okay, students, welcome back. Yeah, we'll continue our discussion. Now, in the energy band model, there are three important or basic principles, starting with the allowed states, then how these are going to be distributed over the energy, and the third one is how many of these are occupied, nothing but the fraction of occupied states at a given energy level at a given temperature. Okay, anyhow, first one we have done with the allowed states. Okay, now let us understand the same information we have already represented with the bond model. Now we are taking the band model. We'll see what will be the correspondence, so that we are representing the same information but in two different ways, that you must understand. Okay, now what we'll consider is correspondence between correspondence between bond model and band model. Okay, so let me represent with bond model first. Okay, so we have taken the two-dimensional representation, something like this. Okay, yes or no? So this is the bond model, I can say. What is this one? This is bond model. First, let us represent bond model. Okay, bond model. Okay, so here at this corner you have a silicon which is bonded with the 4 adjacent silicon atoms. Similarly, this is also one silicon atom there, and it is bonded. Okay, like that. Okay, so this is nothing but the two-dimensional which I have represented earlier. I am following the same. Okay, now how to represent generation here? How to represent the generation? Suppose this particular bond is broken. Okay, okay, so this particular bond is broken. Okay, which releases electron hole pair. Okay, electron, and this vacancy we are calling it as what? Hole. So what is this process? We are calling it as generation process. Let me represent with capital G. Capital G is what? Generation. Okay, now let us consider there is some free electron is present somewhere here. Okay, so this is the free electron. Okay, and let us take there is some vacancy that is going to be present. Okay, so this is the vacancy that is going to be present. Now what can happen? This electron, free electron, can come and occupy this vacant position. This electron is coming from in the crystal structure, which is moving very freely, and it is coming and occupying the vacant position. So what is this process you will refer? It is called recombination. So in the bond model, this is how we can able to represent the generation and recombination of the electron hole pair. Am I clear? Yes. Now let us consider the band model. Let us consider the band model. Okay, now how we can represent this? Let us take, this is the bottom of the conduction band and this is top of the valence band. So this is EC, this is EV. Okay, so like what is the representation that we have given? I'm following. Okay, so EC, EV. Here ET is the top of the valence band. You can take it as up to infinity, no problem. Okay, we'll see why it is infinity later. And this is EV, which is the top of the valence band. So your valence band is from minus infinity to EV. Conduction band is from EC to infinity. You can take. Okay, so minus infinity to EV is the valence band. EC to infinity is the conduction band. Hope I am clear. Okay, and what is this? This value is the energy gap. Difference between EC and EV is the energy gap. Now, how you can represent the generation in this? How you can represent the generation? An electron from the valence band is moving into conduction band. Okay, and there is a vacant position which is the hole. So dot represents here electron. This circle represents what? Hole. So this process is nothing but what? I can call it as generation process. Now what about recombination? How you can represent recombination? An electron which is present in the conduction band is coming into the valence band and occupying a vacant position here. Okay, so this process is nothing but what? Recombination process. You can both are representing the same information but in two different ways. The first one is with respect to the bond model. The second one is with respect to the band model. You can see that. Okay. Now suppose if you are moving in the upward direction, if you are moving, suppose this is the electron, you are moving in this direction, what it indicates? What it indicates? Electron gaining kinetic energy. Electron gaining kinetic energy. Okay, or you can say conduction band electron if you want. Okay, and similarly here also, even in the valence band, if you consider when you are moving in this direction, upward direction, what it indicates? Electron gaining kinetic. Okay, and what about hole? Suppose if you consider the hole, if you are moving in this direction, this is hole gaining kinetic energy. Why it is downward now? So what is your this axis here? What is this axis? What is this axis? Is the electron energy E. So electron is a negatively charged particle. So if you represent that as you are moving, okay, in this direction, upward direction, the electron energy is increasing. What about hole? Hole is a positively charged. How to represent that hole energy is increasing? It is moving downwards. Okay. Yes. So this is the correspondence between the bond model and band model. Okay. Hope I am clear. Okay. So with this, the first principle that we have considered is going to be completed. Okay. Now let us move to the next one. What is the second principle that we need to consider? What is the second principle? Distribution of allowed states. Okay. Distribution of allowed states over energy. Okay. So it is also called as, simply I can say, density of states. I can say simply what? Density of states. Okay, it is also represented with what? Density of states. Okay, so this is represented with, we have already given what is the term? N of E, with N of E. So what is this called? Density of states function. Density of states function. Is it clear? Okay, now let us consider, okay, the energy band diagram that we have represented. From that we'll try to understand how they are going to be distributed. Okay, so please concentrate. Whatever we are discussing in case of intrinsic semiconductor material, these are going to be repetition in the extrinsic with little modification. Okay, so again there I'm not going to spend a lot of time. Okay, here I'm clearly explaining what these are going to be. Okay, so please concentrate. So here, anyhow, default, please remember this is the electron energy, even if I am not representing it. Okay, so what is the conduction conduction band? How you can represent? Let us take, this is top of the conduction band and this is bottom of the conduction band, EC. And let us take, this is top of the valence band, EV, and this is bottom of the valence band, EV. Okay, let me repeat this notation. EV is what? Top of the valence band. EB is what? Bottom of the valence band. EC is what? Bottom of the conduction band. ET is top of the conduction band. Okay. Now, if I want to represent the density of states function here, okay, throughout the conduction band, let us take throughout the valence band, one simple relation is not going to be sufficient, or one single relation is not sufficient to represent this distribution over the complete, either conduction band or valence band. Okay, but our interest is going to be only at the edge of the conduction band and edge of the valence band. Am I clear? Okay, so let me write that point. Okay, a single mathematical relation, or function, you can call relation, is not sufficient to represent the entire conduction band, okay, or valence band, okay, valence band function, okay, valence band function. But practically, our interest is at the edges of the band, either valence band or conduction band. Our interest lies at the edges. But with one simple relation or single relation, you cannot represent this function. Okay, with one simple equation we cannot get it. Okay, but what is the a point of interest for us? It is edge of the conduction band and edge of the valence band. Okay, so at the edges of the band, let me write one more point. At the edges of the band, the distribution, can be represented, with a parabolic approximation. Okay, is it clear? Yes. Okay, only at the edge we can use what? Parabolic approximation. Okay, so if that is the case, we can draw this something like this. Okay, the distribution of the energy is going to be in the valence band. Let us take, it's going to be something like this. You can represent. Okay, now coming to the conduction band, this is going to be much more difficult than your valence band, so I'm not going to complete it now. Okay, so let me write that point also. The representation are so the distribution, is not as simple as in the one second. The distribution is not simple in the conduction band, compared to valence band. Okay, but anyhow, again our interest lies where? At the edge of the band only. So at the edge, again here also in the conduction band, you can use the parabolic approximation. Okay, hope I am clear with what I have explained. Yes. Okay. Now this is what N of E is going to be. This is what N of E, and this is what N of E. Okay. Now you need to understand one important point here. Okay, we need to give the units also. Let us please concentrate. Now if I want to find out how many number of states are present within an energy interval, okay, suppose you consider this is the energy interval that I am going to consider. Let us take it as DE. Yes. So how many number of states are present? How many number of states? It is DE into N of E. Am I correct? It is DE into N of E. So you are talking, when you are talking about the distribution of the states, it is over an energy interval. Please try to understand this point. Okay. How many number of states are present within an energy interval? Okay. Then what could be the units of N of E now, if that is the case? What are the units? N of E is going to be per centimeter cube per electron volt. Please try to understand this. The units are going to be what? Per centimeter cube per electron volt. Why? It is within this energy interval, how many number of states are going to be present. So how many number of states is within the volume per centimeter cube. Now this is electron volt. Okay, so that's why what is the units of this? Per centimeter cube per electron volt. Okay, so please, this is important point. Okay, what are the units? Okay, hope I am clear. Now, for your understanding purpose, I will explain with a numerical. Suppose you take a silicon, if it is a silicon material, okay, how many number of atoms are going to be present per centimeter cube? It's going to be 5 into 10 power 22. Am I correct? 5 into 10 power 22. Okay. Can I have how many number of valence states are going to be present? So this is atomic density, and each atom is going to have 4 valence electrons. Please try to understand. Each atom is going to have 4 valence electrons. Now can I say 4 into 5 into 10 power 22? If we take total area here under this, what I am going to get is nothing but per centimeter cube. That is important. 4 into 5 into 10 power 22 per centimeter cube. So these many number of states are present if I take a silicon atom. So how you get this? There are 5 into 10 power 22 per centimeter cube of atoms, okay, within the volume, and each atom is going to have 4 valence electrons. Now how many states you should have? 4 into 5 into 10 power 22 per centimeter cube. Hope I am clear? Yes. Now here you need to understand one more important point, that if you see the band structure that we have written here, the density of states thing, you can very clearly observe that at the edges of the band, either you consider valence band or the conduction band, at the edges the number of available states, okay, density with respect to density I'm talking, number of available state within an energy interval are going to be less. And as you are moving towards the center, this is going to increase. Okay, so let me write that point. So what it is, at the edges of the band, at the edges of the band, it can be conduction band or valence band, the number of states within an energy interval. So this is important, okay, within an energy interval less, and this is increasing as we are moving, as you are moving towards the center of the band, okay. So band means either it is conduction band or valence band. You can very clearly see from this. Okay, so this is the, suppose you take this one, no, this energy, this is the edges of the band, EV are the edges. So you consider, and at the middle you consider, you can very clearly observe that at the edges the number of available states within energy interval are less, and as you are moving towards the center, this is going to increase. Okay, so please here, my point of interest here is you must understand how they are going to be distributed and how we can represent this N of P function. Okay, okay, so up to which part you require, that I am going to explain here. Okay, because there are a lot of other quantum physics that we must understand here which is not required for us. So that is the reason why I am not going for those things. Okay, am I clear? Now how to represent this value here, that we need to understand. Okay, so this N of E, now I can write it as this N of E, some constant A1 into under root, okay, E minus EC I can write. Okay, let me write, I'll give that. Similarly here, some constant A2 into under root EV minus E. Okay, see why I'm writing here E minus EC is, what is the lowest possible energy in the conduction band? EC. And in the valence band, what is the highest possible energy? EV. That is why you are writing EV minus E here, E minus EC. Okay, hope I am clear. Now these constants you can get, what is this A1 is. Okay, let me write A1 and A2. This A1 is going to be 8 root 2 pi, okay, 8 root 2 pi Mn whole power 3 by 2 divided by h cube. Okay, let me write A2 also, and then we'll explain what the terms are going to. A2 is 8 root 2 pi mp whole power 3 by 2 divided by h cube. Okay, so mp here, effective masses of electron and hole respectively, and h is what? H is a constant. Okay, am I correct? Okay, it's a Planck's constant. Okay, now what is Mn and Mp here? Mn and Mp are effective masses of what? Electron and hole respectively. Okay, Mn and Mp are effective masses of electron and hole respectively. Okay, so here the important point what you must understand here is, with a single equation it is very difficult to represent the complete variation of your density of states within the conduction band as well as within the valence band. But our interest is going to be at the edges of the band only, because we are making some approximation. What is that approximation? We are calling it as parabolic approximation. Okay, so that is why I am representing like this. Okay, and another important point what you have to understand here is, at the edges of the band, the number of available states within an energy interval is going to less, and as you are moving towards the center, this number is going to increase within an energy interval. Okay, so these points are important, so please keep it in mind. Okay, now let us move to the very important one. Okay, the next principle, what is that? The third principle that we are going to consider. Please concentrate. This third principle is going to be very, very, very important one. Okay, you must understand here. Going to be helpful for many other discussions that we are going to make further. Okay, what I am considering, fraction of occupied states. Fraction of occupied states. Occupied states at any energy level E, or given energy level E and temperature T. Fraction of occupied states at any given energy level, okay, and the temperature T. So this is represented with a mathematical function called as Fermi-Dirac distribution function or Fermi-Dirac probability function. Okay, so it is given by f of E comma T is equal to, okay, f of E comma T is equal to 1 over 1 plus e power E minus EF divided by KT. Okay, so what is this called? This is called as Fermi-Dirac distribution function. Fermi-Dirac distribution or Fermi-Dirac probability function. Probability function. Okay. So what is the maximum value of this f of e comma t? 1, because it is a probability function. It should be 1. Okay. And there is one more term which is appearing here, which is called as, EF. What is this called? Fermi level. Very, very important one. Okay. Later we are going to see, based on this Fermi energy level, we can able to solve many number of problems, and we can able to understand many number of concepts also. Very important one. Hope I am clear. Okay. Now let us understand what this is going to be. Okay. So anyhow, this is under equilibrium. You can add here this function, whatever you are written is under equilibrium. This is default. Okay. Under equilibrium. Anyhow. Okay. Now let us consider this further, and we'll try to understand some important factors. Okay. And how to represent this f of e comma t with respect to temperature. If the temperature changes, okay, the characteristics is going to change. We'll see how. Okay. Now let us start with the analysis at absolute zero first. Okay. Now I am considering at T equal to 0 Kelvin. Please try to understand some important conclusions that we are going to make from this discussion. Okay. So at T equal to 0 Kelvin I am considering. Okay. Now first I am considering, for example, you take E less than EF I am considering. Okay. What is the temperature that I am considering? Absolute zero. And I am taking E is less than EF in this equation. Okay. Now since this T is zero, this term can become infinity or minus infinity, becoming depending upon the sign of E minus EF. I'll repeat this point. Since T equal to 0 Kelvin, this factor E minus EF by KT can become plus infinity or minus infinity depending upon the sign of E minus EF. Am I correct? Now if E is less than EF, this is minus. So minus value divided by 0. So it is minus infinity. Am I correct? If this is the case, E minus EF divided by KT is going to be minus infinity. Then what is the value of f of E comma T? It's going to be 1. Okay. Now let us have discussion with mathematical things first, and then conceptually it is going to represent. Is it fine? Okay. Now let us consider the second case. Okay. Consider the second case that I am going to consider now. E is going to be greater than EF. If that is the case, we can very clearly see E minus EF divided by KT will become infinity. So this is e power infinity is infinity. 1 by infinity will become 0. So f of E comma T will become 0. Hope I am clear. Yes. Okay. Now physically what this is going to represent? Physically, what is the meaning of f of E comma T is equal to 1? Try to think physically what f of E comma T is equal to 1 is going to represent. What is f of E comma T we have given? It is the probability of finding an electron at a particular energy level E and given temperature T. Okay, let me write that. E comma T is, okay, f of E comma T, okay, represents probability, okay, probability that a particular energy level E, okay, is occupied, okay, or you can say filled. Occupied, also you can call it as what? Filled. Occupied by an electron, okay, at a given temperature T. At a given temperature T. So hope I am clear. Yes or no? So it's a probability function. So if I say f of E comma T equal to 1, what is the meaning of that? That particular energy level is occupied with the electron. Hope I am clear. And if you say f of E comma T is 0, what is the meaning of that? It is unoccupied, or otherwise I can say it is not filled with the electron. Hope I am clear with whatever I have explained. Yes, if f of E comma T is 1, it indicates that that particular energy level at a given temperature T is occupied with an electron. And if f of E comma T is 0, it indicates that that particular energy level is going to be an unoccupied state. Okay, fine. Now let us consider, okay, let me draw that graph here, okay, and then we'll go for the further discussion. Okay, so what I'm going to plot here is, please, this is very important one, try to concentrate. Okay, so here this is f of E comma T, I'm taking x-axis, and this one is going to be what? E minus EF, let us take, or energy also you can take anyway, okay, E minus EF. Okay, now let us represent. So f of E comma T ranges from 0 to 1. Now this is 0, okay, let us take this is 0.5 and this is 1. Okay, now what about this one? This is actually E minus EF. No, I'm taking, because you can see the in the expression I have E minus EF, or you can take the energy also, there is no issue with that. Okay, so here this is, let us take this is minus 0.3, minus 0.2, minus 0.1, 0, let us take 0.1, 0.2, and this is 0.3. Okay, that is E minus EF in electron volts. You can have, anyhow, default it is in electron volts. Am I clear? Now let us draw for the 0 Kelvin, and then we'll go for, if you increase the temperature, what will happen. So from the discussion that we made, you can very clearly see that if E minus EF, okay, let us take this one, E minus EF, okay, so E less than EF means what? Can I say E minus EF less than 0? E less than EF is nothing but what? E minus EF less than 0. So what is f of E comma T? It becomes 1. So if I take any value of below this 0, its value is going to be what? 1. F of E comma T value is going to be 1. And if you go for this one, that is E greater than EF means E minus EF greater than 0. Am I correct? Okay. See, this is nothing but what? Can I say E minus EF less than 0, and here E minus EF greater than 0. Yes or no? Okay. So if E minus EF is greater than 0, what is f of E comma T? 0. Nothing but for these values it should become 0. Hope I am clear. Okay. Now let me represent that. Let me represent. Okay. So if it is negative, okay, nothing but E minus EF is less than 0, the value should be 1. Let me represent with the dashed line first. Okay. Please try to concentrate. This concept is very, very important one. Okay. Now what about above this? It should become 0. Am I correct? And what is this? Is nothing but E minus EF equal to 0, this one. Yes or no, this reference. And this, whatever the graph that I have plotted now is going to be for T equal to 0 Kelvin. Okay, am I clear? T equal to 0 Kelvin we have plotted. Now, let us take, I am increasing the temperature. Now what will happen? Okay, what I am considering now? Slowly increase the temperature. So what will happen? Now whatever the function that we have written now, f of e comma t is equal to 1 over 1 plus e power e minus ef divided by kt, no? Now here t is not 0, it has certain value, okay? Yes, certain value. Now if you go for this e minus ef less than 0, earlier what we got, f of e comma t is 1, but it is not 1, it is going to be less than 1. Please try to understand this point. Similarly, when you go for e greater than ef, that is e minus ef greater than 0, f of e comma t is not 0, it's going to be greater than 0. What is the reason? We know very clearly that when you increase the temperature, okay, because of the thermal energy, electrons from valence band can move into conduction band. Am I correct? Okay. Now, please try to understand this point here. What is the meaning of this, physical meaning of this one? What is E minus EF less than 0? Is nothing but you can say Fermi, valence band I can consider. All the energy levels which are present below EF. And this is conduction band. So this indicates that f of e comma t equal to 1 is going to indicate that all the energy levels which are present below the Fermi energy level are filled. And what about this? All the energy levels which are present above the Fermi energy level, they are going to be empty. At what temperature? 0 Kelvin. Now when you start increasing the temperature, what is happening? Electrons are moving from valence band to conduction band. Now you can able to see the electrons which are present in the conduction band also. So f of e comma t is not 0, it is greater. And in the valence band you can find some unoccupied states or unfilled states. So f of e comma t is not 1, it is going to be less than 1. Hope I am clear. Let me repeat this point, please concentrate. At absolute 0, if you consider, from this discussion that what we made, f of e comma t equal to 1 represents here that all the energy levels which are present below the Fermi energy level are filled, and all the energy levels which are present above the Fermi level are empty, because f of e comma t is 0 for that condition. Now as you increase the temperature, some of the electrons will move from valence band into conduction band. So you can find some electrons in the conduction band also. So f of e comma t is not 0, slightly greater than 0. And you can find some of the states which are present in the valence band which are empty. So f of e comma t is not 1, it is slightly less than 1. Hope I am clear. Okay. Now how to represent that information in this? Yes. You can very clearly see now. Suppose if this is the value, no, negative values if we consider, it is not 1, it is slightly less than 1 now, slightly less than 1. And here it is not equal to 0, slightly greater than 0, slightly greater than 0. Okay, so please try to concentrate how I am drawing this diagram. Okay, slightly it is greater than 0. Okay, and here it is slightly less than 1. Am I correct? You can very clearly observe here. In this region, the value of your f of e comma t is not 0, slightly it is greater than 0. And what about here? It is not equal to 1, slightly less than 1. And whatever the increase I am having here, that much of decrease I am going to have here. Okay, so let me draw symmetrically here. Okay, so whatever increase there, same amount of decrease, because it is a probability function. No, total area should be equal to 1, area under this curve. Okay. Now, if you suppose increase the temperature further, what will happen? More and more number of electrons can move from valence band to conduction band. So you can find more number of electrons are there in the conduction band, and in the valence band you can find more number of vacancies or unoccupied states. So can I draw like this now? Can I draw like this now? Please try to understand how you are getting this. Okay, so whatever the increase I am having, say that much of decrease I am going to have here. Okay, now if you further increase, okay, so what will happen? If you further increase, what will happen? If you further increase the temperature, okay, so like this I am going to get. Okay, hope I am clear with whatever the graph that I have plotted now. Okay, let me name these values. Let us take, this is for temperature T1, this is for temperature T2, this is temperature T3. So here T3 greater than T2 greater than T1. Okay, so this is how the f of E comma T is going to change with respect to temperature. Because of that, the carrier concentrations are going to change. Okay, hope I am clear. Okay, so we have started with 0 Kelvin. From that we are giving this analysis. Okay, so this graph is very important one. Okay, try to understand. Many times we are going to use this. Okay, here one important point you must understand here. I'll write here. You can very clearly see that f of E comma T is symmetrical. Okay, is symmetrical with respect to EF. Okay, even though I have written here E minus EF, no, what is E here? EF. That is what I am writing. F of E comma T is symmetrical with respect to what? EF. What is EF? Fermi energy level. Okay. Now here I want to clarify one thing, that usually on the x-axis we will take the variable, and on the y-axis we will take the function. Usually that is the graph how we are going to represent. Am I correct? How you will represent the graph? X-axis is going to represent and y-axis is the function. But here I am putting in the opposite way. Actually this is the function. F of E comma T is the function. And what about this? This is the variable here. E minus EF. E minus EF is the variable. And f of E comma T is the function. What is the reason? If you see the energy band diagram that we have discussed, what is the y-axis? Energy. It is always energy. So later we need to overlap, or we need to represent the three different information, starting with allowed states, then distribution of allowed states, and fraction of occupied states on one graph. So what is the y-axis for all the three? It is the energy. That is the reason why I am taking x-axis as what? Function, which is f of E comma T, and y-axis is the variable, which is E minus EF, or simply energy you can call it. Okay, so hope I am clear. Okay, now let us understand some point here. What is the physical significance of the Fermi energy level? We'll try to understand. Okay, yeah, you can take this point. This is very important. I'm writing physical significance. Physical significance of Fermi energy level EF. Okay, so the discussion that we made, we can very clearly see that if you consider this one at absolute zero, we can very clearly see at absolute zero all the energy levels which are present below the Fermi energy level, they are filled or occupied states, I can say. And the energy levels which are present above the Fermi energy level, they are going to be unoccupied or empty states, I can call. Okay, so let me write that point. at absolute zero, right? Absolute zero, all the energy levels, okay, which are present above, okay, let me write in brackets below, okay, so start with below first and then we'll, okay, which are present below, let me write in brackets above, okay, correspondingly I'll write, okay, below the Fermi level, okay, at absolute zero, all the energy levels which are present below the Fermi level are what? Occupied, okay, and in brackets I'll write unoccupied, okay, occupied states. Please try to understand, okay. I'll read like this: at absolute zero, all the energy levels which are present, okay, which are present below the Fermi level are occupied states, and if you read above, then correspondingly you read in the bracket what they are: unoccupied states. Hope I am clear. Yes, okay, in that way you can read. And one more thing, okay, for T greater than 0 Kelvin, okay, now if you put in this equation T greater than 0, put E equal to EF, what will be the value of F of E comma T? 0.5. Am I correct? T is greater than 0 now, but E is equal to EF I am considering. Then what is the total value of F of E comma T? This will become 1. So 1 by 1 plus 1, which is 1 by 2, 0.5. So I can write, okay, EF is the energy, okay, EF is the, okay, at which exactly, okay, exactly half of the available states, are occupied, okay, half of the available states are occupied, okay. But what is the condition here? You need to understand this, okay. I'm not, first one which I have given is at absolute zero, the second one is for T greater than 0 Kelvin, okay. So hope I am clear. So this is the physical significance of the Fermi energy level, okay, EF. So hope I am clear. Now there will be one approximation that we are going to use in the semiconductor theory frequently, okay. Let us concentrate on that. We'll try to understand what it is. It is called as Boltzmann approximation. What it is? Boltzmann approximation. Please try to concentrate, okay. So what it is? Boltzmann approximation, because we are going to, many times it is default, we are going to consider this Boltzmann approximation, okay. Whether this approximation is valid or not, we'll check it later, okay. See, any approximation you consider, it is valid under certain conditions, okay. You have to check that condition. Anyhow, for our application purposes in practical, is going to hold for, all the temperatures. That we'll prove it later. Let us consider, okay. Now this is valid, okay. This is valid, okay. The first condition is, okay, valid for E minus EF, okay, is greater than 3 kT, okay, or E minus EF by kT is greater than E minus EF by 3 is greater than kT. That also you can write, okay. So E minus EF by kT is greater than 3, or E minus EF greater than 3 kT, or E minus EF is less than minus 3 kT, okay. So we'll check how it can be, okay. What is the final result that we are going to get if I get this approximation, okay. Let us write. We know Okay, f of e comma t, no, consider f of e comma t, what it is? It is 1 over 1 plus e power e minus ef divided by kt. Okay, now let us consider the first condition. Okay, what is the first condition? Let e minus ef is greater than 3 kt. Okay, now with this condition, can I approximate this value? We can very clearly see e minus ef is greater than 3 kt means this exponential term is going to be the dominating term now. Okay, so now can I say, which implies e power e minus ef divided by kt is much greater than. Okay, so that I am going to neglect 1 from this. So what is the final equation that I can write here? F of e comma t is equal to e power minus e minus ef divided by kt. Okay, yes, yeah, please don't try to by heart any equation, try to understand how you are getting. Okay, so if you know the Fermi-Dirac distribution function, from that I am getting. So here for e minus ef greater than 3 kt, you can very clearly see that this exponential term is the dominating one. Compared to this, one can be neglected, so that I am going to get this. Is it fine? Now let us take the second condition. What is that? E minus ef is less than minus 3 kt. E minus ef is less than minus 3 kt. Okay, now if that is the condition, please again consider f of e comma t. What is f of e comma t? What it is? 1 over 1 plus e power e minus ef divided by kt. Yeah, here please don't do that, because e minus ef, no, this exponential term is negative, no, e minus ef divided by kt is going to be much less than 1. Okay, so don't neglect this term and put f of e comma t equal to 1. Don't do that. Okay, why? We have done the same thing earlier, no, why can't be here? You must understand not only mathematical point of view, you must understand what physically it is going to represent. If you do the same thing here by if you neglect e power e minus ef by kt compared to 1, what we are going to get? F of e comma t equal to 1. What f of e comma t equal to 1 is going to represent physically? Certainly that particular energy level is going to be occupied, but it is not the case. Okay, so then what we can do now? So we know very clearly the binomial expansion, no, 1 plus x whole power n is approximately equal to 1 plus n into x. Okay, but what is the condition? What is the condition? X is less than 1. Okay, that we can apply here. So what I can write now? F of e comma t is equal to, can I say 1 plus e power e minus ef divided by kt whole power minus 1. Now you can very clearly see e power e minus ef by kt is going to be less than 1, because e minus ef is negative. Yes, so what I am going to get? E of e comma t is equal to 1 minus e power e minus ef divided by kt. Please try to understand what these terms are going to represent in the equation. Okay, yeah, in the previous also you put this is fb, because I am applying the Boltzmann approximation. No, let us put fb. Yes, so why whether this 3 kt, okay, whatever we are taking 3 kt, no, whether this is valid or not, we'll check it later. Okay, because we need some more information also, because we don't know where to be present till now. So once we got that, then we can explore and we can decide whether this approximation that we are going to use is going to be valid or not. Okay, hope I am clear. Yes, okay, so I'm doing very simple mathematics. Okay, you need to thorough with the mathematics. Very simple mathematics I'm using. Okay, so please get thorough with that. Okay, now we can take a note here. Like earlier, we have used a Fermi-Dirac distribution and then we are approximating. No, so what could be the difference between the two? Physically, what will be the difference? Maybe mathematically or as a numerical values you see, finally you may get the same. But physically, what is the difference? You must understand. So if you consider Fermi-Dirac distribution alone, okay, then no two electrons, okay, can occupy the same energy level. Fermi-Dirac distribution function assumes that no two electrons can occupy the same energy state. But whereas Boltzmann approximation assumes that any number of electrons can be occupied, okay, any number of electrons can be present in a single energy level. Okay, so let me write that point. Okay, Fermi-Dirac derivation, Fermi-Dirac derivation, okay, assumes that no two electrons, okay, no two electrons can occupy the same energy level or state, okay, but okay, whereas Boltzmann's approximation, okay, assumes that any number of electrons okay, any number of electrons can occupy the same energy level, okay. Now this is the physical difference between the two things, okay. This is the physical difference between the two, okay. So mathematically you may get the same results, okay, but almost same, but physically this is the difference. So Fermi-Dirac distribution function assumes that no two electrons can occupy the same energy state or level, but whereas what about Boltzmann's approximation? Any number of electrons can be occupied by any number of electrons can occupy the same energy level. Okay, so this is the physical difference between the two. Okay, so hope I am clear with okay that whatever the things that we have discussed now in okay energy band model. Okay, now we'll go for the doubt clarification. Okay, please so here why I'm stopping here is next topic it will take more than half an hour. That's why I'm stopping. We'll continue with the tomorrow, but anyhow if you have any doubts you can ask me. Please again I'm requesting you, okay, if your doubt is get clarified, please down your hand and unmute your voice, okay, because I'm getting a lot of disturbance. Okay, so yeah. Yeah, one more clarification I want to give. See, doubts I can clarify. There is no what you call, I don't have any objection. Okay, but my suggestion from my side is, okay, you spend at least some time so that if you get clarify these doubts on your own, you will never forget. There is no silly or great doubt. Doubt is doubt for everyone. Okay, but it's not the case. Okay, you need to spend a good amount of time. That is my intention. Okay, I will clarify your doubts. There is no issue. Okay, but finally what you are going to get is very important one. You may not realize now, but later on you may feel for that. Okay, yeah, fine. We'll go ahead with the Doubt clarification. Sudeep, please go ahead. Sudeep. Yeah, Varji.
Hello, good morning, sir.
Very good morning.
Sir, at page 38F.
30?
8F.
38. Yeah, please.
Sir, in this second principle is distribution of energy state or allowed state.
Okay, you can say distribution of no energy is, we can call default, it is allowed only, no? Okay, I'll correct it. Okay, distribution of allowed states. Fine, thank you.
Sir, at page 41F.
One second. Distribution of, yeah, allowed states, I can say. Page number
41F.
Yeah.
So as you said, we are decreasing the interatomic distance.
Mm-hmm.
So, but how we are decreasing any significance? How we are decreasing that interatomic distances?
See, how you are decreasing is how you will form a crystal.
Sir.
How you will form a crystal structure.
Yes, sir.
In the crystal structure, what is the interatomic distance?
Okay, so by the formation of crystal.
Yeah. For your understanding purpose, I am taking that we are considering the isolated atom, n isolated atom, and then we are decreasing all those things I'm talking. But it is not you are doing, no, already material has its property.
Okay.
Material, it is already happened.
Okay.
Yeah.
So in this diagram only, thus what is the region between black line and the second green line? What the region is this? What region can we say?
Yeah, it is only in the semiconductor only, no? Any type of, see, one particular semiconductor, we can have a atomic separation with the dashed line, black dashed line have represented, no? It can be. Now, any other material can have somewhere here you can have the interatomic distance. Then in some other material, it may be the interatomic. Depending upon that, energy gap is going to change. We can very clearly see that.
So basically is a range of the crystals and atoms.
Yes. No, not the crystals and atoms. No. If you depending upon the how you are deciding the interatomic distance, I've given one point. No, what is that? See this. It depends on the total number of attractive and repulsive forces must cancel each other.
Forces.
And system should possess minimum possible energy, minimum total possible energy. Based on that, you are going to this value. Now it varies from material to material. Okay. Yeah.
Okay. And sir, why electrons are not allowed in forbidden gap?
Why?
Why electrons are not allowed in?
There are no allowed energy states that are going to present. If energy level is there, it can present.
So it's a fact, means it's a fact that it is not allowed.
Yes. That's what I'm telling you. There are no energy levels, so it is not. There are no electrons. It's a fact.
Okay, sir. Oh, and sir, H page 50F. 50.
Yeah.
Sir, in that second equation, what we wrote at T greater than 0 Kelvin. So in there we have to also mention that E is equals to EF. Then only we can say that it is the half of the available states.
I have written no. EF is the energy at which exactly. What is the meaning of that? EF is the energy at which means what is the meaning of that? E is equal to EF only, no?
Okay, sir. Okay.
Clear?
Okay, sir. Thank you, sir.
Okay. Yeah, Sudeep. Yeah, please respond fast, Sudeep. Yeah, Abhisha Sahu.
Hello.
Yes.
Sir, am I audible?
Yes, yes. Go ahead.
Sir, I have a doubt on 41F page.
41F.
Yes, sir.
Yeah.
Yes. So that red line, sir, how can we recognize that this will mean 6 state, so 8 state?
6 where 6 states?
So that red line, the branches one.
Yeah. See, in the 3P level, how many number of states are present?
So 6N.
6N.
Yes,
These
sir.
6N are going to split first.
Yes.
Am I correct?
Yes, sir.
3S, how many states are there? 2N.
2N.
Now these 2N states are splitting here.
Yes,
So
sir.
up to this, dashed line, green dashed line I've represented. There is no mixing of these 6N and 2N. That's why this is separately 6N I have represented. Here it is 2N. And after that, what is happening? You cannot separate now.
Yes, sir.
So total, how many are going to be?
8N state.
That's what I've written.
So after that green line, sir, this one is 4N state.
Again, yeah, it's actually, you can call it a factor experimental results. Okay. After that, the energy band diagram looks like this. What will happen is, again, these 8N states are going to be split into 2 bands.
Yes, sir.
So one band is going to consist of 4N states. The other one is going to consist of another 4N states.
Yes, sir.
Okay, and separated by an energy gap where there are no energy levels that are going to be allowed or electrons that are going to be allowed.
Yes.
Okay, fine.
Yes, sir. Yes,
Yeah.
thank you, sir.
So, yeah, Krishna, please go ahead.
Hello, sir.
Yeah,
Hello?
please. Yes, go ahead.
Sir, in page 29F.
29F.
Sir, here in photo generation, when both the atoms combine, the excess energy is released in the form of heat, right?
Yes.
But in Auger recombination, how will the excess energy release as, sir?
That energy will be given to either electron or hole. If either electron or hole is not taking, it will be dissipated as heat.
Means either electron or hole means which other than these two which are vacant, right?
Obviously.
Okay, sir. Thank you, sir. Sir, and another doubt is, sir, we considered that probability case, na, sir.
Which one?
Excuse me, sir. In concentration of electrons and holes.
F of E comma T, na?
No, sir. First one, P.
Okay. Yes. Tell me.
There initially we told that P is the probability that they are going to collide. But the same T again you are using for intrinsic semiconductor. How, sir?
See, that's what I told you. What you have to understand is the concept. Notation, usually probability, you will use P. Now, P is actually, we are representing for concentration of holes also. So, depending upon where you are using, are you getting my point?
Okay.
Depending
so both P are not same, right?
Yes, definitely they are not the same.
I thought both are same, sir.
No. That's what I clearly mentioned. Notations are your convenient way of representation. It may change or it may be different. Yeah.
But same number of electrons are it is required in both the cases.
In the both the cases means what?
Because 42 we took, na, sir. In one case it is for colliding to generate EHPs, and in another case it is used for intrinsic concentration.
See, you are mixing two things. Please listen carefully. In intrinsic semiconductor material, N is equal to P is equal to Ni. What N represents here? Concentration of electrons.
Yes, sir.
P is concentration of holes.
Yes, sir.
And Ni is intrinsic carrier concentration.
Yes, sir.
Now, later on, we have taken that small p as the probability. Okay. So, now why you are mixing P power 42 and P?
So, but you only wrote, na, sir, P for 42 equal to 10 power 10 by 5 power 22 in the before page.
Okay, fine.
But how? They the 42, what will in the earlier case 42 represents number of particles that needed to collide.
42 is the number of particles. Yeah.
Here also same 42 we are taking as sir for intrinsic also. Then
no man, Ni, see the expression. You are you able to see the expression this?
yes sir.
Ni is what?
Intrinsic concentration.
What P represents here?
So here also the same particle. Okay.
See, I have very clearly mentioned what is the probability that a particle collides. I have very clearly. Are you getting?
Yes sir. So
Okay.
to generate electron hole pair or for concentration, the particles must collide.
Come again.
So so we can conclude that to generate an EHPs or to form any intrinsic semiconductor concentration, there is a need of particles to collide, right, sir?
Yeah, not necessarily. Okay, this is only one way of getting your electron hole pair. There are the other ways also.
Okay.
It is not necessary. Okay.
That energy band diagram, sir.
Page number.
Sir 30. Sir 39 F I hope, sir. Next one.
Sorry, okay, 41 F, no problem. Yeah.
41. Sir, is it? Will it be for any orbital? Will it be the same representation, sir? That first it will combine and again it will divide.
Obviously, this will happen. Outermost orbits will interact first, and then next levels, and then next levels. Yeah.
So it is completely based on experimental, nothing theoretical.
No. You have some theoretical, understanding. You need to go for quantum physics now. It is not required for us. It is not required for us. That's why I have not touched that.
Sir, and two more doubts, sir. Last doubt, sir.
Yeah.
Sir, at T equal to 0 degree, at absolute 0, does pure semiconductor and intrinsic semiconductor acts like insulator? Is it true, sir?
Yes.
But extrinsic will not act, right?
No, extrinsic also will become insulator at absolute 0.
So all semiconductors will, but it will be having impurities, na, sir. Extrinsic.
What we'll discuss now. Extrinsic will go there. We'll discuss. Will be get
clarified. In scattering phenomenon, won't the particles collide?
See, collision. There are two types. Both are called as collision. That's what I mentioned. No, recombination as well as scattering. Both are called collisions. Recombination, there is a physical collision. After collision, both electron and hole will disappear. I have very clearly written no statements also. In case of scattering, it is action at a distance. It is also a collision, but it is action at a distance. There is no physical...
But they will not meet, right? But they will not meet.
Action at a distance.
Your voice is not audible, sir.
Sorry. If I say action at a distance, what is the meaning of that? There is no meeting only.
There is no meeting of both the particles.
Yes.
Okay. Yes. Thank you very much, sir. Thank you.
Yeah. Yeah. Vishaka, please go ahead.
Hello, sir.
Yeah.
Good afternoon.
Very good afternoon.
Sir, I have doubt in 30F.
30F.
Yeah.
Please.
30.
Yeah. 30 only, no?
Sir, I'm not getting the second point. In case of a recombination and electrons and hole meet physically after collision, means electrons and holes are colliding, or after recombination of electrons and hole, they are colliding. I'm not getting it.
No, I'm not getting your question. Please ask again.
Sir,
don't get excited. Okay, I'll clarify it out. Okay, please go very slowly. Yeah.
Okay, sir. So in second point, it is given that the recombination of electrons and holes meet physically. Okay,
fine.
And after collision, both the particles are disappeared, right?
Yeah.
So, sir, if the electrons and holes are colliding, or electrons after recombination are colliding?
Recombination itself is collision. That is what now we are giving. Try to understand the first statement what we have given. Both the processes are collisions. Okay. Now this collision can happen physically or may not meet physically also. So if they collide and they disappear, okay, then it is a recombination. And there is one more process also. Electron can scatter the hole. Okay. And the important, later we are going to anyhow discuss this. It is not, guarantee that at every point when electron hole meets, there can be a recombination.
Okay. So, sir, you are also stated that it is disappeared. So, how?
Once recombination happens, can you?
I'm not getting that point after collision.
See, once recombination takes place, can you see that electron and hole now?
But sir, after.
No, answer my question. After collision, after recombination, electron. What is a recombination? Electron is coming from conduction band to valence band.
Yeah.
Now, can you see the same electron and hole?
Okay, you mean it will not present in that conduction band?
Obviously.
Okay, so here disappearing means it is disappeared from that conduction band, right?
Means, okay, disappear means you are thinking from the crystal structure it gone, huh?
Okay.
No. From the conduction band it is gone. See, that's what you must understand. See, where the free electron is going to be present?
In conduction band.
If I say disappear, where from it disappeared?
From conduction band.
That's it.
Okay, sir. Sir, I have next out in 49F.
49F.
So could you please explain this diagram, because I had some disturbance, I'm not able to listen.
You won't complete? Okay, fine. Listen. Have you understood the T equal to 0 Kelvin diagram?
Yeah.
Now what will happen is, suppose you increase the temperature, what will happen? The valence electrons will get energy and they will move from valence band to conduction band.
Yeah.
Now, according to the discussion that we made, if you see this equation here, okay, if E is less than EF, for T equal to 0 Kelvin, F of E comma T is 1. What is the meaning of that? All the energy levels are filled. Am I correct?
Yeah.
Now, because of increase in temperature, what happened? Some of the electrons has been moved from valence band to conduction band. What is the meaning of that? You can find some empty states in the valence band also. Now, it is not equal to 1. Definitely, it should be less than 1. Am I correct?
Yeah. Yes, sir.
Come to this E greater than EF. At absolute 0, F of E comma T equal to 0 means all the energy levels above this are going to be empty. There are no electrons. But when you increase the temperature, what will happen? Electrons has been moved from valence band to conduction band. Now you can see some of the energy levels which are filled. Now can I say F of E comma T is slightly greater than 1? Sorry, slightly greater than 0? Yes?
Yeah. Yes.
Yeah. That is what I have represented here. You see the red color which I have given here. So you see after 0, immediately after 0, you can find here, this is the positive value, E minus EF is greater than 0.
Yeah.
This portion, am I correct? So it is slightly greater than 0. But what about here? It is slightly less than 1 in this edge. So whatever increase I am having here, that much decrease it should be there, because it is the probability density function. What is the area under that? 1. Yes or no? So that is the reason why. And if you keep on increasing, what will happen? More and more number of electrons can move from valence band to conduction band. Then increases. That is what we have represented with the blue and another gray color.
Okay, sir.
Fine?
Okay. Yeah. Thank you, sir.
Yeah. Sudeep, please go ahead.
Hello, sir.
Yeah.
Sir, I had a doubt in 37F.
37F. Yeah, please.
Here, sir, could you explain how you got Ni is equal to capital N into 1 by P e power minus e power kT? I didn't understand that capital N. How did that come?
What is the previous page you go?
This only, sir. I had a doubt here. Yeah. How did you get the atomic density into the equation?
See, where from you get the intrinsic concentration? From the atoms only, no?
Yes, sir.
Okay.
But how do you know it's a multiplication of this factor?
Okay, see here, the 34F you see.
Yes, sir.
Have you understood this? P power 42?
Yeah, this part I understood, no doubt.
What is 5 into 10 power 22 here?
The number of silicon, the number of...
Can I say atomic density?
Yeah.
What I have written there?
Oh, okay, it's the same thing. Okay.
The numericals I just converted into some equation. Got it?
Yeah, got it.
Okay.
Sir, one more doubt, sir. I think this has been explained before, but still in 41F, sir.
41F, please.
Yeah, could you just explain the splitting process again, sir?
See, 5 times I explained, man. Now also two or three times clarified, no? Okay, but anyhow, listen carefully. When you start decreasing the interatomic distance, the outermost electrons are going to start interacting, okay?
Yeah.
Now, according to the Pauli's exclusion principle, no two electrons should have the same energy.
Okay.
Now, if you see here, suppose the blue line which I have represented earlier, okay? All the 6n electrons, sorry, all the 2n electrons which are present here, we have the same energy here. At one particular energy, 2n electrons are going to be present. But there are 6n states, please remember that.
Yeah.
But 6n states have the same energy.
Okay.
Now, according to the Pauli's exclusion principle, what will happen? No two electrons should have the same energy means what? These 6n energy levels, now they have to split. Okay, but maybe a little difference will be there from one energy level to another level. That is what we have represented as this when they are splitting.
Yes, sir.
Got it?
Okay.
And as you are keep moving, keep decreasing that interatomic distance, you can observe this type of variation.
Okay.
Okay. So how you are deciding atomic separation depends on the what number of total attractive force and repulsive force must cancel. Based on that, this will be decided. Okay.
Sir, but how do you in the upper state there'll be 0 electrons and in the lower state you'll have 4n electrons?
See the second principle that we have given here. What is this?
Electrons occupy the lowest energy states available.
So in this diagram, which are the lowest energy levels? Obviously below 4n, which are there, they will be filled first. If remaining is there, then they will go to the higher energy levels.
Okay.
Got it?
Yeah. Thank you, sir.
Okay. Yeah, Gautam, please.
Sir, good afternoon, sir.
Very good afternoon.
Sir, I just want a small clarification. Yesterday, when we were discussing about the free electrons and bounded electrons concept, there is the thermal excitation energy KT responsible for that?
Obviously. That is what I told many times. When T equal to greater than 0 Kelvin, there will be energy for the atom as well as the any particle that is going to be present.
Yes, sir. And there is a relation. So there is a relation between that KT and temperature in Fermi-Dirac.
Temperature in Fermi. How come Fermi-Dirac came here?
In Fermi-Dirac, like the probability of finding an electron above.
That's see f of e comma t. I have very clearly mentioned what are the parameters. No, f of e comma t means what? It's a function of energy.
Sorry, sir, your voice was off.
F of e comma t means what? It's a function of energy and temperature.
Yes, sir. This temperature is at 300. If we consider the temperature at 300 Kelvin.
Not only 300 Kelvin, any temperature you consider.
No, sir. For example, if we consider 300 Kelvin, the Fermi curve will not be a perfect square, no, sir. We'll be having some density of probability of finding electron above EF is more than below, no, sir.
Okay.
So can we think that the thermal energy KT, this is the reason for that?
This is the reason for that means I'm not getting your question.
I mean, how free electrons are able to move bounded electrons out of their covalent bond?
Free electrons will not move bounded electrons, no? Who
No,
said?
sir. I mean, when they collide with them.
Which are colliding with what?
When free electrons in a crystal lattice are colliding with the bounded adjacent bounded electrons.
Not always. Collisions will be there always, but energy should be there now. I have given very clearly when the covalent bond is broken, an electron hole pair will be generated. You should have at least the energy gap, then it can happen.
Okay, sir. Got it, sir.
Okay.
Yes, got it.
Yeah, Tejashree. Tejashree.
Good afternoon, sir.
Very good afternoon. Please.
Sir, I have a doubt in page 41F.
41F.
Yes.
Hmm.
So, you said the distribution of the energy level into discrete level is due to decreasing the interatomic distance, right, sir?
Yeah, when you decrease the interatomic distance, there will be an interaction between the outermost orbits.
So, why there is a need to decrease the interatomic distance?
How you will form crystal structure? How you will form crystal structure? If you consider n isolated silicon atoms, can you call it as silicon crystal? Yes. Could you
No.
hear me?
Yes, sir, I can hear.
Please respond. Can you call it as crystal?
No.
Then you have to see, for your explanation purpose, we have taken n isolated atoms and then start decreasing like that. We are explaining, but actually it's a natural phenomenon, no? Am I correct?
Your voice is breaking, sir. I couldn't hear you.
For your explanation purpose, you are taking n isolated atoms and then you are decreasing. But actual thing is what? Physically it is already there, no? Naturally silicon crystal has been formed already.
Okay.
Is it fine?
Yes, sir, I got it.
Mm-hmm.
And sir, another doubt, sir. So, where is the vacuum level actually present in this diagram?
Where it's not required here, that's why I not represented. It will be somewhere. You take where EC is present. EC is present here, no?
Yes.
From that, it will be depending on material. It will be some certain value. See, all these things are imaginary, no?
Okay.
Can you show it on any crystal? No. For our understanding purpose, we are having some representation.
Okay.
Got it?
Thank you. Yes, sir. Thank you, sir.
Yeah, please. Gudur 1450471. Please.
Good afternoon, sir.
Very good afternoon.
So page number 28F, sir.
28F. Yeah.
Sir, no, sir. 44F. Sorry, sir.
44F. Huh?
Yes, sir.
Hmm.
Sir, if electrons move towards conduction band, means their energy will increase, sir.
Not only towards conduction band. When you go in the upward direction, electron energy is going to increase because that is what we are representing, no?
Okay, sir.
What is y-axis? Electron energy.
Electron energy. Okay, sir. If holes will go downwards, means the energy will.
Yeah, Kalyan Kumar.
Hello, sir. Good afternoon, sir.
Very good afternoon.
Sir, I have a doubt in page number 42F, sir.
42F, please.
Sir, you have written some statement in the note, no, sir. Atomic separation. Can you explain that statement, sir?
What explanation you want?
How could you tell that separation is decided by attractive forces, sir?
Then which is going to decide how when you are suppose there are one particular system is there, how you can hold suppose there are 3-4 different components are present, how you can form a system? One has to hold the other, no?
Yes, sir.
Correct?
Yes, sir.
So that in when you are talking about here, there will be attractive and attractive and repulsive forces between different particles or different atoms that are going to be present, no?
Yes, sir.
That is what I have given here.
Okay.
Attractive and repulsive forces.
Okay, sir. Thank you. Sir, I have another doubt, sir. Sir, in the second point, sir, distribution of allowed states. I think it's page number 44, sir.
Okay. No, it's not 44.
No, not this, sir. I think 45, sir. After this. Sir, how could you explain the density of state functions at valence band and conduction band, sir?
How could you explain? I have explained already, no? I'm not getting your question.
No, sir. How can you? I could not. How can you write this, sir? That they are parabolic approximations.
See, these are quantum mechanics that we need to consider. That's what I very clearly mentioned. No, if you go for quantum mechanics and study, and then you can get to know all these things. But for your purpose, it is not required. That's why I'm directly representing here to make you to understand few things, because again, these things are going to be very much important to understand the other concepts. Are you understanding?
Okay, okay.
So there are a lot of quantum physics that you must understand to understand the semiconductor physics also. But for our purpose, we may not require all those things. So if you go and read about quantum mechanics or quantum physics, then you can get to know all these things.
Okay, okay.
Is it clear?
Yes, sir. Thank you.
Sai Charan. Sorry,
Sir.
Sri Charan. Please go ahead.
Sir, I have a doubt that why we should take 42 particles, sir?
Why?
42 particles. Exactly why 42?
Have you listened why it is 42? How you got 42?
Yes, sir, I listen, but a small confusion, sir.
Where you have confusion? Tell me. Where it is? Yeah, see this.
Yes, sir.
What is the average particle of an energy? KT, no?
Yes, sir.
Now it is, we have calculated at room temperature, it is 0.026 electron volts.
Yes.
Now each silicon bond strength is how much? 1.1 electron.
Yes, sir.
Correct?
Yes,
now,
sir.
If I want to break a covalent bond, we very clearly mentioned that there are different particles that may converge to a particular point, or in terms of waves, if you talk, they will interfere. Am I correct?
Yes, sir.
And if that energy is equal to the bond strength, then it will be, that particular covalent bond will be broken. Yes?
Okay.
Got it? Now,
Yes.
if each particle is having an energy of 0.026, how many number of particles are required to have an energy of 1.1 electron volt?
Sir, if the KT value changes, our
No,
particle.
see, 1 second. First answer my question, then we'll go for next.
Yes, sir.
If each particle is having 0.026 electron volts, how many particles are required to have an energy of 1.1? Obviously 1.1 divided.
Yes, sir. Approximately.
Yeah, that's what I told. 41 point something you will get. For round it off, I had taken 42.
Yes, sir.
Yeah, now we go for second round.
If the value of the KT changes, the number of particles also changes, sir.
Obviously, no.
It is not exact. If according to the question, we should change the number of particles.
If they have not mentioning any temperature, it is a room temperature.
Okay.
Default it is room temperature.
Doesn't mention anything. We should take 42 if they mention. We should calculate.
Default value. Not only here, there are some default values. It is better to remember. Anyhow, they will mention, but it is better to remember also.
Okay. Thank you.
Yeah. Yeah, Manisha.
Hello.
Yeah.
Sir, page 41F.
Yeah, everyone have doubt in 41F. Fine. Go ahead.
So here, between the two green dotted lines, it is the crystal separation only for the metals. And the black dotted line is for other than metals, sir.
No, once your second green is there, no, here.
Yes.
You start moving to the left. It's going to be for semiconductor materials. Because you can very clearly see that at the beginning itself we represented for metal or conductor there is an overlap conduction band and valence band, no?
Yes, sir.
But whereas in semiconductor, okay, or insulator also, but insulator will have a higher energy gap. These are separated. Got it?
Okay, got it, sir. Thank you, sir.
Okay. Yeah, last year.
Hello.
Yes.
Sir, page number 53F.
53F. Now.
Sir, here you told that no, sir, Fermi Dirac derivation, no two electrons can occupy the same energy level. And Boltzmann approximation, they occupy the same energy level. Where did we take this, sir?
Means?
Where did we take this approximation before?
Where you have applied, huh? No, No, still we have not applied. I have given the Boltzmann approximation. Have you listened this? How we have explained Boltzmann approximation?
Yes, sir.
This we are going to, later on in our discussion, we are going to consider this Boltzmann approximation. Still I have not applied, just I have given.
Okay.
And this is going to be applicable or applied in many situations. We are going to consider.
Okay, sir.
Got it?
Yes, sir.
Yeah.
Thank you, sir.
Okay. Shiva Sai.
Yes, sir. Sir,
Yeah.
in page 41F.
Oh, 41F. Go ahead.
Sir, is the diagram is for silicon crystal?
No, I have started with the silicon only. No, what is the example that I have taken?
I mean, it's a crystal or an isolated atoms.
No, I'm not getting. No, this is not for crystal, man. See, that's why I very clearly mentioned. No, see the first one, this one. This is for an isolated silicon atom. No, only one atom is there.
Yes, sir.
Then I have drawn for the n isolated atoms. And this is for what? This is for the crystal.
Yes, sir. Sir, once the crystal is formed, then we can say that bonds are also formed.
Obviously,
yes.
how
Sir,
your
then-
atoms are going to hold? One atom will hold the other.
Yes, sir. Sir, once bonds are formed, every atom should have 8 electrons in its valence shell, no, sir.
1, 8. Come again. Every.
Once bond is formed between every atom, every atom should have 8 electrons in its valence shell, no, sir.
8 electrons. How come 8 electrons will come?
Octet rule, sir.
Octet rule? Where you are applying this octet rule?
Sir, I mean.
See. 1 second, please. If you consider the silicon atom, how many number of valence electrons will be there?
4, sir.
4. If they form a bond to adjacent 4 silicon atoms, how many are going to be?
Sir, once bonds are formed, then each atom will have valence.
That's what
of
I'm asking you, man. If individually, if you consider silicon is having 4 valence band, am I correct?
Yes, sir.
If it is 4 adjacent atoms are there and it is forming the covalent bond, how many atoms will be there?
Total 5 will be there.
5.
5 atoms, sir. 5 atoms.
I'm not. See, can you separate only 5 atoms from the crystal structure?
No, sir.
That's what I'm telling you. If silicon atom is there will be 4 adjacent silicon atoms, and there is a covalent bond. Now, how many number of electrons will be there in that system for that particular silicon?
Sir, whatever the number of atoms may be, but each atom will have 8 electrons for sure, sir.
No. How it can be 8 electrons? Please go and refer. Where you read this?
Sir, it's general chemistry, sir. Sir, any atom will to become stable, it will acquire 8 electrons, sir.
That's what I'm talking, man. Please try to concentrate what I'm asking and answer the question. Individually, if I take a silicon, how many number of valence electrons are there?
4, sir.
4. Fine. Now this silicon is going to form a 4 covalent bonds, no?
Yes, sir.
How many number of electrons will be there in that, no? For a particular silicon atom?
8, sir.
That's what I told. Then
Sir,
what is your doubt?
Sir, my doubt is in this diagram in 3p, every state should be filled. I mean, there are vacancies, no, sir.
How it will be filled, man? That is what I'm telling you. If you take the rightmost part, still it is isolated. Please try to understand. Rightmost, if you go, still it is isolated. Once it is isolated, from that what you are doing, you are keep on decreasing the interatomic distance, then this structure is going to form. Whatever the atomic separation that we are representing here, at that point it is the crystal. Are you understanding?
Okay.
Are you understanding?
Yes, sir.
Got it. What you are thinking is 8. You are seeing the rightmost part where still there are n isolated atoms. Still there is no crystal structure that is formed.
Okay, after this line of crystal separation, the atom will form.
Yes. Then
yes.
only crystal structure will form.
Okay, sir. Thank you.
Okay. Kalyani, please go ahead.
Good afternoon, sir.
Very good afternoon.
Sir, in the same page, you said this the black dotted line represents the crystal separation or atomic separation. That means the eight n states are divided into 4n states, resulting in 4n electrons and 0 electrons in up and down states. Are these 4n electrons available for another atom to form a bond?
Already bond has formed. No, see, when you form a crystal structure, is there bonding between the atoms or not?
Then when these 4n electrons are out of the crystal separation,
where 4n electrons are out of the crystal structure?
You represented in outside, no sir.
Where? Which part you are talking? This one, huh? Upper side, huh?
Down part, sir.
Not outside, man. See, I have put it the arrow mark. No, there I cannot able to write. That's why I put it here. 4n states, 4n. Have you seen the arrow mark here?
Yes, sir.
Can you see the arrow mark?
Then do they belong inside the crystal separation only, sir?
Yes, obviously. Valence band, where it is going to be present? Valence band or conduction band still is related to the crystal structure only, no?
I thought after the atomic separation, these are available for another atom to bond to form a covalent bond.
See, that's what the next page I have given one important statement here. The atomic separation in a crystal is decided by the fact that all the attractive and repulsive forces are going to cancel each other. Am I correct?
Yes, sir.
Okay.
Yes, sir.
So this is decided. This whatever line black dotted line I have given. This is the crystal separation or the atomic separation. That is the separation. That's all.
So there won't be any bond formation from the crystal separation.
No. Why? Your question itself there is no base. Already bond has been formed. No, when you are decreasing the interatomic distance, obviously there will be a bondage between the different atoms. No.
Okay, sir.
Are you getting? When you decrease and you are fixing certain interatomic distance, already crystal structure has been formed. Means what? Atoms are holding. No, one silicon atom is holding another 4.
So it is neutral now.
Which one is neutral? Always,
the whole crystal structure.
Obviously, otherwise it is not under stable condition.
Okay, sir.
Okay.
Thank you, sir. Sir, another doubt, sir. You said that in the recombination collision, the electron and hole pair will disappear. Do you mean that disappearing of electron and hole pair, like, are they coming back to the vacant places in the conduction band, sir?
That's what vacant, not in the conduction band, in the valence band. If you see the 1 second, if you see the that whatever the correspondence between where it is, 1 second, correspondence between you see here how we have represented generation and recombination in the band model. Generation means electron is moving from valence band to conduction band.
Yes, sir.
Recombination means
the electron is
coming from conduction band, and in the valence band there is a vacancy that is occupied.
Yes, sir.
As simple as that.
So this indicates the disappearance in recombination.
Yeah, disappearance means it is disappearing from the conduction band.
Oh, okay, sir.
Okay, I think same.
Ultimately, it is ending up in valence band.
Obviously, it has to, because you have excited from the valence band. It is a stable state for electron.
Yes, sir.
And it is unstable in the conduction band, so it has to come back to its original or stable position.
Okay, sir. Thank you, sir. Yes, sir.
Yeah, Mahidhar, please.
Sir?
Yeah, please.
Sir, yesterday in the concept of hole, we have seen that at the temperature greater than 0 Kelvin, we observe some vacant in the bond model, vacancy. So, in order to form the bond vacancy, we have to excite something with equal to the bond strength, no, sir?
Yes, obviously.
So is the thermal energy enough to form that vacancy, sir?
Yes. Now, see, that's what today we have discussed. No, to break a covalent bond and to generate electron-hole pairs. Okay, we have given that 42 particles has to convert at room temperature.
Yes, sir.
So that is actually happening.
Okay.
That is what exactly happening. Okay. Okay, but there I cannot able to explain. That's simply I have given there. Then with the details we are discussing now.
And also in the Boltzmann approximation, how did you tell that it is approximately equal to 3 kT, sir? Greater than or less
That's
than?
what we are taking. Why we are taking 3 kT? We'll see it later, because till now we don't know where the Fermi energy level is. No, depending upon that whether it is valid or not, we need to.
Okay, sir.
Fermi
And
energy is
also
level,
the-
we can check.
In the bound electrons and the free electrons, we can say that the bound electrons mobility is less than the free electrons, sir.
Obviously, that's what we have written mu n greater than mu p. No, mobility
And
of
also,
electron
what
is.
can we comment? And also, what can we comment on bound electrons and hole mobility, sir? They are in opposite in direction.
What is hole actually? What is hole? What is hole?
When the electron transfers from valence to conduction, the hole forms.
In terms of bond model, you talk. In terms of bond model, you talk. In terms of bond model, you are talking in terms of band model. You talk in terms of bond model. If there is a breakage in the breakage of the covalent bond, there is a vacant position. Am I correct?
Yes, sir.
Now, how actually? What is the actual scenario that we have represented? Actually, the bound electrons are moving, not the bound electrons are moving via the vacancies.
Yes, sir.
But to make our convenient way of representation, that hole we have taken as the vacancy. Now we can very clearly see that electrons and the hole, they are moving in the opposite direction. Vacant position is moving in the opposite, so it is the opposite direction. Then what could be the mobility of bound electron and hole?
It can be almost be same.
That's what. That's all. You have given question and as well as the answer also.
Okay.
Got it?
Yes, sir. Thank you.
Okay. Prabha?
Sir, I have doubt in page 31F.
31F. Fine. Please.
Sir, here you said KT is equal to 0.026 electron volts, sir. Is that for temperature 300 Kelvin?
That's what now. Can you see me here? I have written a T equal to 300 Kelvin. Can you see me?
Yeah. So if I substitute the Boltzmann constant and temperature, it's not equal to 0.026 when I calculated manually.
How much you got?
I got 1.1 and 10 powers also.
1.1.
Sir.
You try to calculate. Okay, you will get it. Please. Which K value you have taken?
8.62 to 10 power minus 5.
Substitute. You will get it. Definitely, you will get it.
Okay.
Hello, sir.
Yeah, please.
Sir, page 42F.
Please.
Sir, how did you write that note, sir? Note point.
What is that? Please read it.
I didn't. The atomic separation that I didn't understand, sir. It said that all the forces should cancel. Means what, sir?
Not all the forces. Attractive and repulsive forces.
Can
you consider, if you consider any system, will you have, particularly for electronics, you will have attractive and repulsive forces will be there?
Sir, your voice is not audible, sir.
When you consider the crystal structure, can you find attractive forces and repulsive forces?
No, it will be in stable state only.
When it is going to be stable state? Once the crystal structure has been formed, then it is going to be in stable system.
Yes, sir.
But what we have given here, we have started decreasing the interatomic distance and we are forming. In that process, is your all the forces will at a particular position or particular point of time, this will happen.
So when we decrease the atomic distance, there will be forces, that is attractive and repulsive forces. So finally, when a crystal is formed, all forces will be cancelled and the electrons will occupy the lowest energy state.
Yes, obviously.
Sir, and another doubt, sir. Sir, we have written that in Boltzmann one note we have written, sir. Fermi-Dirac approximation assumes no two electrons can occupy same energy level.
Okay.
Sir,
Yes.
how do you write this note, sir?
Fermi-Dirac, how we have derived in all the assumptions that we made according to the Pauli's exclusion principle, no two electrons should occupy. But we are making some approximation here. I have explained 3 kT approximation.
Here we are in Boltzmann's we have to that approximation, sir.
That's why in the Boltzmann approximation, any number of electrons can occupy the same state.
Means within the 3K, within that 3K range, we can have any number of electrons.
Any approximation is valid under certain conditions. That condition we have given for the Boltzmann.
Okay, sir. It is based on experimental analysis, sir.
Yeah, experimental, and it is a quantum physics concept actually.
Oh, the entire node point. Okay, sir.
Yes. Not only entire, many things that we are discussing, we are taking from the quantum physics.
Acha, okay, sir. Okay, thank you, sir.
Yeah, Shubham, please. Shubham Gaikwad.
Good afternoon, sir.
Very good afternoon.
Sir, page number 41F.
Please go ahead.
Sir, in last, if there are 3n electrons are present, then how will be the distribution?
I'm not getting. Come again.
Sir, in 3p state, there are 2n free electrons.
2n electrons.
2n electrons. But if instead there are 3n electrons, then how will be the distribution?
How come you will get 3n electrons?
Sir, suppose in case of arsenic there is 4p3.
So yeah, it will be you make it out of these 6 states, 3 will be occupied.
Yeah, then energy distribution will be how?
They will change. See, it will change, man. It will change. But can you they are going to be the experimental things and all. For your understanding purpose, I have given by taking the example as 4th group element. You do the similar type of analysis by taking that. Are you understanding? The concept that you must understand or you must concentrate here is what my intention is. You must understand how the valence band and conduction band has been formed. If I simply draw this diagram, which I have represented here, okay, it's going to be not useful for you. That's why I have taken with an example and I have explained.
Okay, sir.
From this, you try to explore the things, okay?
Okay, sir.
Are you getting my point?
Yes, sir. Yes. Thank you, sir.
Yeah. Okay, we'll meet tomorrow sharp 9 o'clock. Thank you.